So upon the field, we might put what's called an ordinary, which is a simple geometric charge which always has the same location. So you can see on the right, there's a list of a whole bunch of different ordinaries, but the way that we would use them is that we would start with a background, azure, meaning blue, a bend argent, a diagonal stripe white or silver. We can also introduce divisions. We don't always want the field just to be one basic thing. Instead, we want to divide the field into different parts. And so these will often be per some ordinary. So per bend, per chevron, per fess, per pale, per saltier. That's dividing along the line of an ordinary. Here we have quarterly, or an azure, a bend gules, meaning divided into quarters, yellow and blue, a diagonal stripe red. The final thing I want to introduce is the mobile charge. And this is something that's a charge of arbitrary design, which is not restricted in its location. So it can really be anything. I have several examples here, a boar, an estoile, a griffin, and so on. But it can also be a rock or a computer or whatever you want it to be. This is where things can be kind of anything arbitrarily. And so again, I have a blazon here, sable, a bend between 3 estoiles or, sable, a black background, a bend, diagonal stripe, we know. 3 estoiles are these 3 small stars. Now, we don't just want to have simple charges, but we also want to describe the charges. And we use that, we do that with what's called an attitude. For example, this lion can have several different attitudes. It can be rampant, it can be passant, sejeant, and all of these other ones to describe in what position it is. So with all of that, we can finally put together a more complex example. Similar to what we had before, quarterly or an azure, which is to say, divided into quarters, yellow and blue. On a bend gules, 3 lions passant or. On the diagonal stripe red, 3 lions walking forward, yellow. So I'll give you 10 seconds to review the vocabulary that we've learned so far, and I'll take a drink of water. Okay. So those are the basics. Now I'm going to introduce you to the rules. Now, when I say rules, what I mean are guidelines, right? This is an art, and so you can't really apply rules to art. I mean, you can, but they're guidelines and conventions. And specifically, they are the guidelines and conventions proposed by some people in the 1850s and 1920s. So we're limited here in both time and space. And moreover, this is all kind of via my interpretation. They did not give formal specifications. They gave, English words mostly. And so there's a little bit of gray area in a lot of this. But with that said, the first rule, the rules are divided into 3 categories, or I've divided them into 3. The first is style, which is to say, is the blazon itself elegant? Does it sound nice when you say it? Then there's validity. Does it make sense at all? And then there's tincture. Is the result pretty in some sense? So the first style rule is that no charge can be given an inappropriate attitude. So vert, a lion, rampant, argent, that's fine, right? We saw rampant, that means rearing up. But rampant is only a thing that predators can be. Here we have a stag, and stag is prey. And so when we have, something's not coming up. Oh, there we go. So when we have stag, a stag cannot be rampant. Instead, it needs to be springing, or what we call salient. And in the same way, a lion cannot be salient. It needs to be rearing up. So there are certain words that you have to use depending on what charge you have. The next rule is that no tincture can be named twice. So this blazon that I presented earlier breaks the rules because we said or twice, and that's not allowed. That's considered inelegant. And so instead what we do is we use an index to index back into our list of tinctures and say, we named or first thing, and so we're going to say of the first to describe that first tincture we named. And of course, you can do of the second and of the third and so on. So those are the style rules. Then there are validity rules. This, again, recall that rampant means rearing up. And so the idea of a plow rearing up is, well, if you're creative enough, you can think of it, but generally we don't describe plows as rearing up. And so things like this, or even worse, saying an apple is rearing up or whatever, it's just nonsensical. And so you can't have an invalid attitude in that sense. Another rule is that we want to avoid index out of bounds errors. So if we have a blazon like this, where we say per pale argent and sable on a fess or a lozenge of the fourth, we named 3 tinctures, but we said of the fourth, this doesn't make any sense. And so we need to disqualify this blazon as well. Now, the most important rule of heraldry, or at least the earliest one learns, is the so-called rule of tincture. And the basic idea is that you can't have a color on a color, and you can't have a metal on a metal. And so if you have something like this, where we have a field gules and a bend azure, this breaks the rule, because we have a color on a color. On the other hand, if you have something like this, which is arguably uglier, it's actually okay. Fur on fur is allowed, and it's explicitly allowed by some authors. This, again, illegal, because this is a metal on a metal. But if you have a color on both a metal and a color, that's actually also allowed. So it's a very simple rule, but there's a lot of little nuance to it. So here are, again, a quick review of the rules of blazon. And now that we have these rules, we can formalize. So here is a grammar of what I've called mini blazon, a very small subset of the entire world of blazon. I'm not going to get into the details of what all of this is. Instead, I will just say that with this kind of formal language, we can get to a type system. And specifically, the type system needs to do 4 things. It needs to check the attitudes of all the charges. It needs to check that the tinctures are named only once. And it needs to check the references to tinctures. And finally, it needs to check the rule of tincture that we described before. So the type system, again, I won't get into too much detail, but it looks like this. Instead, I will give a short demo, or I'll pretend to give a demo from screenshotted pictures of my terminal. So we have an implementation that is kind of a read evaluate print loop, and we can put in a blazon like this, which says align rampant argent. You'll recall that this one is okay. Lions can indeed be rampant, and so we get okay. If we say a stag rampant, that you recall is illegal, and so we get invalid attitude. This one, quarterly or and azure, blah, 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 or we name or twice, so we get another error, repeated tincture. This one, again, index out of bounds error, so we get a nice undefined tincture reference. And this one, your design from many years ago, this one, you get a rule of tincture violation. So you deserved all the hate you got online. This is inappropriate. Now, with the implementation, we can perform an evaluation. So there's a corpus of about 50,000 blazons written in 1874, or long before that, but published in 1874, called Papworth's Ordinary. Actually, it has this very long name here, but people call it Papworth's Ordinary. And so we went through this and selected, well, not selected, randomly transcribed about 2,000 of them. And of these 2,000, we can parse with the implementation about half. And of that half, 972 of them type check according to our type rules. Of those, we had 9 violations of the no repeated tincture rule, and we had 24 rule of tincture violations. Then there were 20 other errors, which were rules that I wasn't able to talk about in this talk, but we can talk about afterwards if you're interested. And that's all. So in summary, today I presented to you Blazon, the rules of Blazon, and a type-safe version of Blazon with a theory, implementation, and evaluation. In the paper, there's a lot more. There's an extended introduction to Blazon, a complete set of rules, the full grammar that I kind of skipped over, as well as a discussion of methodology and a lot more examples. And that's all. Thank you.
Question, and we are going to run over to the session.
I commented the question.
Yeah.
My comment is, that is so cool.
Oh, thank you.
I encourage you to write that up very thoroughly and make it available, because I can imagine many first-year teachers would want to take advantage of this as an example or exercise for their class. I think it will do really well for them. The question I want to ask is, from these descriptions, you generated pictures. Sometimes it's clear that the picture is uniquely defined, but if you have one of these, I can't remember the name, things that can be freely placed.
Right.
So is the picture uniquely generated? Is that specified by the rules, or are there additional variations? And then how do you deal with that?
Okay, so there are two things. First of all, I did not generate any images. All I have is a type checker, and the images there were actually generated via a program called DrawShield, which does does everything except the type checking. It's a non-type safe generator. For the other part of the question, so yes, there's a lot that's unspecified. For example, if I say there are 17 stars on a shield, in principle, those could go anywhere. And so some of the future work I'd be very interested in is describing some restrictions on what those, or kind of preferences on what those should be. For example, if you have n stars, usually the way you want to display them on a shield preferentially is in a triangle shape. That's just the way convention is. And of course, that's not in these type rules at all, but that kind of restriction would be very interesting to implement. Yeah. Yeah.
Yeah, very cool. I agree.
Thanks.
Have you tried anything like composing them, like maybe parameterizing them over something and then composing them together? See how that works out.
Can you explain a little bit?
You've got just the, what was it called, the band and then the stars, and then like make a function that takes the background as a parameter, and then try to make a family of
yeah, I mean, that's definitely possible. It wouldn't be Blazon in that sense. It would be some kind of super Blazon language. Yeah, meta Blazon maybe. Yes, yes. Yeah.
Thank you for the awesome talk.
Thank you.
I'm curious, have you looked at when you print your error messages saying, here's a repeated color, use the urgent twice here, whatever. Have you thought about referencing why that thing is wrong? Either, you have a color on a color, and here's the color that you've placed over. Or invalid reference, here are your three things that you named it for.
Yeah, that's definitely possible, and it wouldn't be too hard to add. I'm just kind of lazy.
Sure, yeah.
Yeah.
Last question, and move on to the next topic. For the violations of the rules, when you were looking at those examples, did you find yourself agreeing? By which I mean, have you steeped in heraldry as you are, looked at them and gone, yeah, that is kind of ugly, where'd you have it?
There were definitely some of them, especially the violation of the rule of tincture. It does make sense. You don't want, I don't know, like blue on red is a classic GUI or graphic design faux pas to have blue and red together. And so I do think they do protect you from making some mistakes, but I also think that they're a little bit overboard. I also agree that it sounds better or fancier if you say of the first instead of or twice. But it's just doesn't really matter. Yeah.
Well, let's thank the speaker.
Thank you.
Ready for our next talk?
Yeah.
Generally, you are running this over time, so if you are giving a talk, be sort of hanging out in the wings while we're doing questions.
Thought I had a question. All right.
You can ask it from the wings. That's allowed. It's all right.
Okay.
Sides.
Now, okay.
Yeah. Got it for him.
I didn't know how to do that.
So we use weird words.
No, it's good.
No, I'm not on the internet. I didn't know I needed to be.
We connect to the internet.
How do we connect to the internet?
Yeah.
DVD room?
No.
Okay.
Should I go later? I don't have internet and I didn't know I had to connect to Zoom.
Well,
This.
you have to connect to the Zoom to be able to present.
Right. Okay.
Is this?
Then you
And you asked.
You can just do that.
okay.
Yeah.
That's okay. We're not in such trouble that I have to worry about this yet.
Okay.
So in the meantime, I'll say for those of us who came in during the first talk, glad that you made it. The registration desk was a bit of a line, so I understand folks were waiting there. Thank you for coming in. Again, this is FARM, Functional Art and Music. I'm Milano. And the FARM has traditionally been and continues to be a 2-half conference. We have a daytime half that ends after the first afternoon session, about a 4-hour break, and then a concert half. This year, our concert is in the main concert hall for the Conservatory of the National University of Singapore. This is the kind of place where you would normally expect to see an internationally recognized touring string quartet. But we are going to take it over for our computer music / programming as music concert, which is going to be an incredible experience. It is open generally to the public. It is open to everyone who registered to ICP or Splash, who's in Singapore for fun, who walks in off the street. It is a great place to bring your partners, your friends. When we're at lunch talking to other workshop attendees, remind them that it is fair and it is worth going to. We have a hall seated up to about 450. If everyone who's at Splash tomorrow, ICP tomorrow attends, we will technically be over capacity. I would like to be over capacity. So do what you can to recruit. And if you wind up being an artist that needs to get there early, or if you have trouble finding it, you can always find me on Discord. We have a conference Discord. Just ping me and I'll help it out. Cool. Any logistics questions for y'all, or are we're good? So I'll just give 1 minute more to see if the internet works. We're making progress on the internet.
We're rolling on a hotspot on our friend's phone right now.
That's going to be quite delayed.
Yeah, I don't know what to do about the pin was not working.
Yeah.
Tell you what, maybe we should swap.
Okay.
I can get you rolling while we're doing the next talk, if that's okay with you.
Yeah, that's fine with me.
Is it possible we could be ready to rock and roll?
All right.
All right, let's rock and roll.
However, really clear and we'll do
Okay, well,
fast finish.
perhaps we should be a co-pilots instead. We're so.
I wonder if we should do thirds.
No one's not here either. So we're gonna keep getting set up.
Okay.
You can get clear.
Yeah.
There's here. Let's presume we're gonna rock and roll.
Okay, we're actually gonna go now. If that's okay with you.
Sorry.
Not at
No,
all.
you had no reason to know that. We just have a Wi-Fi issue with the next talk.
Yeah, let's bring it.
Why?
Right, so we have sound in our slides. So,
yeah,
and I'm connected to the
you can
account, so
use this
thank you.
to-
Okay.
Join the meeting so that we can.
Sounds good.
record.
Okay.
Yeah.
Do you have this link somewhere online?
You can use the ID.
Oh, sure. Okay.
Sure.
Oh, wait, then it's both of us. Do you have two mic?
Only one phone.
Okay,
I see.
sure.
Yeah, yeah.
Okay, so we're gonna join.
Switch to the HDMI.
Yes, video, no video.
Yeah, the video is working and
Great.
you can mute yourself and
You join?
share the screen.
Mute self and-
Recording in progress.
Right. Sound is still coming out of here. Oh, but We'll say, okay, hopefully this will work.
Yeah.
We will find out. You'll know if you hear the table of contents that things are working. Yes. Okay. So TBD if the audio will work. All right.
Wait,
Yeah. And we'll plug in the sub.
okay.
Yep.
No, but do we need a
Microphone? Sure. Let's
Uh,
plug it.
Yeah, we might have to share.
The last one was Sans mic. Can you all hear us all right? Okay. Should we do this for the recording? Yeah.
Put that on, you will be silent.
Silent?
for everyone.
Okay. How would you like to do this? What do you think is
Also,
the best way?
let's test your audio.
We did.
No,
Yeah.
we-
For like, we haven't tested it on this system yet, but
You probably should.
we should do that.
Oh, yeah, sorry. Oops.
Let's see.
No, it's totally fine.
Mhm.
No. I muted my own computer, but that's because, I mean, if the set comes out, I want. All right, good enough.
For archival purposes,
All
I
right.
would like to spend 10 seconds to see if we can get the sound to go to the intended destination.
That sounds good. Is someone joined via Zoom who would be able to test that this is audible?
Not that I know of.
Okay. How should we fix
If
that?
it's,
Yes. Okay, so I'll go to the last slide, which is sound.
I can be on Zoom.
That sounds great. Thank you.
Technical difficulties.
Of course, what's happening now is everybody's looking at that shield, wondering if it abides by the rules.
Yeah, I was thinking if we could type something
It
else.
does. Don't think about it.
Yeah. Yeah.
Oh, that's ridiculous.
Hello, we were
Hello,
talking.
testing.
A, we're talking into the microphone, and B, we are playing a sound out of our presentation.
Wait, did you actually play the sound or?
Yep.
Oh, okay.
This has an audio cue attached to it.
Oh, right, right.
All right, A and or B or neither. Talking / this. Okay, maybe the microphone is off, to be honest. But I am. I was told to do that, but I can here. Testing. Okay. Great, but now.
Uh,
Turning this on would help. However, we're doubled up. Okay. Yeah. Okay, great. Well, that's terrific. It's better rock and roll. You might be totally right about that. Thank you. It's been a while. Much obliged. Okay. You self. Okay. Well, everything except this room. But I can just play it out of the computer for that. We're gonna do a little bit of a. So I'm now turning off my computer sound. Need the computer sound option. That does mean there will be an echo because I'm in the Zoom room. Maybe if I. Well, I'm muted, but this isn't, so it's coming out of my computer. But maybe I could just make Zoom not make any sound anymore.
You do that, then you won't be able to hear it.
It's a great point. All right, so we'll just not talk while we play audio. And in the meanwhile, we'll have this really fun echo. And I'm just going to check if I shared sound. Thank you, everyone, for your patience. Great. Well.
All right, team, are we ready to rock and roll?
Most. There's, yeah, okay. Echo out of my computer, but now it's good. Okay. Hello, everyone. Welcome again to Rock and Roll. We're going to try to speak into the microphone. My name is Roger.
I'm Claire. We're both PhD students at Penn.
That's right. And a while ago, we came up with this sort of unusual idea to hear proofs. But before we hear proofs, we're gonna listen to something. Is that the table of contents? All right, that was fun and not expected. Welcome again to Rock and Roll. We're going to first talk about the conception of this tool. We're going to talk about how we applied proof and music theory to build the thing that we wanted, and how we used the language server protocol as well as the MIDI protocol to make this a little easier on ourselves, and then some of the creative design choices we made in hearing our proof. Let's start.
First off, in case anyone here isn't familiar with Rock, it's a dependently typed language. It's a proof assistant. All of us love using it. I love Rock so much that we both love it so much that we were wondering what would this sound like? What would this feel like? Because even though we relate with it by coding and whatnot, can we get more of a body feel with Rock?
Exactly. And this was motivated by a couple of questions. So the first question.
Right. What does the proof sound like? What does sorry sound like?
What do different tactics sound like? The Rock often loop that we do when we're writing proofs is we write something and then we type check it interactively, and it's sort of a conversation between the programmer and the type checker. What does that conversation actually sound like?
And so just like how when you hear something that clearly sounds terrible, like, can we get that too from proofs? If you write a proof that you've been able to QED, like, does that sound correct too? So yeah.
Yeah, or does a bad proof sound dissonant? Also, what does sound better even mean? Does it even mean anything for music to sound good? We'll talk a little bit about this.
And finally, sometimes I'm lazy and I'll use auto and I'll have no idea why my goals are gone. And so I was wondering, like, under the hood, what is happening with auto? And maybe, can we hear that?
So we have a couple ideas to answer these questions. One, what is this conversation like? Well, hearing the sort of tactic response loop that the programmer writes is kind of interesting and can give us a few insights. And it's also just kind of fun. I think it makes Rock a lot more bearable when you get fun sounds coming out of your proof. And fundamentally, this tool is about fun, right? This is an art tool. We have some practical elements that we'll talk about and some maybe things that can give you insights, but primarily this was just to have a good time. Two, yeah. What does it mean for something to sound better? Well, if you want to ask someone what music that sounds good is defined as, or how to define that, first you'd have to define music, and good luck with that. So we decided to use a little bit of dissonance as an indicator of errors, but of course dissonance isn't a bad thing, and it doesn't mean that music sounds better or worse. We're just using it as a heuristic. And finally, this is the one aspect in which we think our tool is somewhat practical. And when you write a Rock proof, for those who aren't familiar, you're trying to solve some proof goal of a mathematical proof. And you might do this very, very exactly with a number of very explicit steps that are easy to read. But Rock also provides some automated reasoning. So it can provide a bunch of these and throw a bunch of them at once at a goal and just solve it for you. And this is really helpful when you have a paper deadline. But when you try to understand your proof, this is not as easy to reason about. You might not know what's actually going on. You can actually break this apart and de-automate it, right? You can print out the individual things, but what these actually are is not always easy to understand. But to understand how much lifting a certain automated tactic is doing, it's actually sometimes easier to hear a complex sound and hear a sequence of notes or a chord rather than look at all these tactics and see which ones are actually being applied. For our proof theory.
Right. So first off, you'll think like, how would this sound like? How would we parse it? So we decided to approach it by tactics. So in a Rock proof, you'll use tactics, which are like, think of it as functions like intros, like intro these variables I want to prove, or apply this existing lemma I want to use. So literally, you can look up what tactics are, but intros, apply, etc. Yeah. And then, so there's not only tactics, but there's also like automated tactics like auto, e-auto, and then there are also things where you can program, you can like we can write code about your tactics, like using semicolon or tacticals like uh, retry, yeah, try. And so we started out with a fixed map of tactics. So there's a lot of them, and we map them to these pitch and velocity MIDI pairs. So first they have like a fixed set of notes, but then given like any kind of proof, like we can parse any given rock file, the sound of the fixed notes will change given the state of the proof.
Exactly. So to summarize, we have a bunch of tactics in rock that are well known, and we map those to different sounds using something called MIDI. This is sort of what a proof looks like, turning individual tactics or lists of tactics into music. How does music theory play into this? Well, we wanted to make things sound interesting and a little bit weird and fun, but not too weird so that you couldn't hear kind of the either consonant elements or complexity elements of an individual tactic. Of course, it's really easy to do consonants with chromaticism. This just means you put things in a scale where basically any two or more notes will sound good together. But we actually decided to abandon this and just let it sound really weird and interesting. Do we really want consonants? The answer ended up being we don't really care. But how do our tactics actually work? Well, auto is a tactic that does lots of things. Maybe it does one thing, maybe it does 20, maybe it does 2. And it does these in sequence, right, over a tactic, or if it's applied to many things, over many tactics. So the idea of auto playing many things as an audio sequence, or sort of an arpeggio, which is a chord where you play all the things individually, auto can kind of take a solo in our thing. You know, auto might play 2 notes, or again, it might play 20. And to jam with your proof when your proof is playing more than 1 note, but is actually playing this sequence of notes, auto gets kind of fun. With semicolon, this is applying many tactics to many sub-goals at once. So if you have a proof that you need to prove some property, and to prove that you need to prove 3 sub-properties, semicolon can apply a tactic to all 3 of them at once. And simultaneity makes us, I think of chords or simultaneous chords, right? Many notes at the same time. Finally, tacticals, which are higher order tactics, which take in a rock tactic and produce something else. So maybe try this tactic, but don't worry if it doesn't succeed, or do this tactic again and again until you can't go anymore. These should probably augment the notes that the tactics already make. So we stay with the bass note, but we're going to raise it by an octave or bend it or do something interesting there. The architecture of this is relatively straightforward. We parse a .v file, that's a rock file, into our rock and roll program. We have a conversation with the LSP, the language server protocol. In our case, we chose to use VSCOC, and that's how we get the notes for the MIDI and also the visual design for the GUI, which we'll be showing off tonight at the performance.
So the language server protocol is a way to universally programmatically interface with programming languages. Sounds all tautological, but basically when you use like an IDE and you have features like autocomplete, or you can search through a complex code base, and you might be using this for a variety of languages, all of that is being communicated using the language server protocol. So in order to parse our rock proofs and actually do something given the proof state, we used one of the rock LSPs. We actually tried both. Coq LSP and VS Cocktop. And we actually ended up using VS Cocktop. So that's the LSP behind the VS Code extension. And then really there's like a bunch of endpoints in general if you want to use this for any language, but we mainly relied on proof view. So if any of you use VS Cocktop on VS Code, it's when you step through your proof and then like right side panel shows up and it shows you the state of your proof and what subgoals you have. And then really, honestly, this is really basic. This did a lot of the heavy lifting work on figuring out what to do given the proof state. And all we had to do was like parse the JSON output. We use JSON RPC messages to send requests and take parser responses. And then sometimes if there was a lot to parse, we made use of Claude Code. So it's very good at just parsing JSON responses. And then finally, So we mentioned like tactics like auto, where under the hood you have no idea what's happening. So already you can at the top of your rock group. Oh, sorry. At the Oh, my bad. At the top of your rock, like this, is this good? Okay. At the top of your rock proof file, you can do set info auto or set info e auto. And then when you get to the auto tactic itself, you'll see on the proof view, like the actual tactics under the hood. So there's a lot of stuff sometimes that can happen. I wasn't even aware of it. And so we take that. So that could actually be multiple different tactics. And then we parse it and send it to MIDI. So yeah, really like if you want to parse any kind of proof, I think not even just using Rock, just like use a language server, use the language's language server, and then you'll get info.
Yeah, the language server was really powerful and can give you a lot of information. Coq LSP gave us less information that was easier to parse. VS Coq Top gives you everything, but it's a nightmare to parse. So it's kind of simple versus everything everywhere all at once. And how much information do you want to get out of your language server? How much do you actually need? We ended up just pulling more and more and more until we upgraded language server protocols because we realized that we wanted to make things really complex and interesting based on the proof state, and we had to use an upgrade. As far as MIDI, so MIDI is the musical instrument digital interface. This is basically how electronic instruments talk to each other. This is used basically globally in electronic instruments. The spec is very standard. And it's a way for us to send little binary packets to a synthesizer, right, an electronic instrument, and get sound out of it. So we generate MIDI in our code base. Rust ended up being better than OCaml for this. We wanted to do this in OCaml. For those who are not familiar, the Rock language is implemented in the programming language OCaml. So we wanted to stay relatively native. But it turned out OCaml was actually pretty bad for MIDI generation. So we ended up using Rust, and we're a lot happier with that. Ideally, in the future, we would actually want to generate MIDI directly out of the language server itself, like out of the VS Coq extension, or even out of the Rock prover. This is a future direction for Rock and Roll 2. For our synthesizer setup, we're using the Teenage Engineering Op1 field, which is a really nice piece of hardware that you can get a lot of fun sounds with, and you'll hear us improvise on that during the performance. GarageBand was surprisingly good for this, though. When we were getting things set up, we used GarageBand as our synthesizer and had a really good time. For now, things are very simple. We're keeping the MIDI single channel and manual ADSR. If you know what those mean, you'll know what this means. If you don't, you can just understand that we're not messing with many of the audio things. But the key point is that we're using MIDI, and that makes us synth agnostic. So this really is a plug-and-play tool. We'll put up a QR at the end. If you have a synthesizer of your own and you'd like to hear what your proofs sound like in that synthesizer, it will work. Finally, the rest of this project, once you've done the LSP and MIDI, is open design space. And we got to play a lot within this space. Because this is an art project too, we had a bit of room for fun. So we didn't initially have a GUI. We just used kind of a text-based thing and ended up writing a GUI, which was a good amount of fun and I think makes the performance much more engaging. We also have an autoplay feature. So if you have a nice long proof and you just want to jam it out in the background, you can just hit go and play it on a track. Listen to it while going to work. And finally, we've tried to make our code base relatively modular and debuggable, so please do PR us and extend it as you wish. So that's it, right? We're done. That's kind of the end of the tool, or maybe not. There are kind of open proofs or open questions. We've talked a lot about dissonance. What is the value of dissonance in a bad proof, in a proof that gives up, or a proof that fails or doesn't type check? It's very funny, right? But maybe is dissonance something that could be appreciated instead of rejected in this tool? Can dissonance tell us anything that the type checker can't? What's on the table for Rock and Roll 2? We talked a bit about this, maybe going direct in the language server protocol. We want to do some things with multi-threading so we can get more complex MIDI and chords. And finally, this is an art project ultimately. And how much of this do we want to turn into a science project, right? Do we want this to be a practical tool where hearing your proof actually tells you some unique information outside of the type checker? Or do we really just want to jam out to our proofs? Right now, we're just going to jam. We're going to play during the performance. And you might learn something about your proof. You might understand that this auto is really doing a lot of heavy lifting more than that one. But for now, we're here to have fun. With that, thank you for coming. Please feel free to scan our QR and PR. We're at time for questions. Right, yes. I'm going to stop.
So as you mentioned, HVR, I'm Phil Father from Edinburgh.
Hi.
Whoa.
That was also very cool. You talked a lot about, does this kind of proof for bad proof or so on sound this way? You have a couple of examples you could run so that we could see it, a nice proof and a.
Yes, for time, we're not going to do that now, but I will be happy to show you offline. I know, yes, we
And for context,
do.
we are listening to a concert like this.
Yes.
Yeah, we're
so during the
playing
performance,
tonight.
Here are some good proofs and specs.
yes. Please do come. Yeah.
Jeffrey Young, Epic Games. This isn't really a question, it's more a suggestion, but I'd be interested to know what the concert C compiler sounds like.
Oh yeah, so we will play a longer example of a sophisticated and well-known rock proof. It's not from Concert, but you may recognize it. And Concert is probably for rock and roll too. So catch you next year.
I'm interested in
Yeah.
going through some old papers that you had used rock to prove things and hearing like, oh, well, all the Stephanie lyrics work is like hardcore.
Ah, yes.
Like,
What's their musical style, you know?
Is plastic.
Yes. We actually have enjoyed doing this just a little bit, right? As we're tightening up the tool. Now it's like sort of time to play and have fun. And playing different proofs has been really interesting, right? Some things don't sound as musically interesting because it's like 30 module imports. You call one command and your proof is done, right? But if you're building things from first principles, you very often get this iterative, expansive music performance really for yourself. It's a really good question, right? And then of course that differentiation is going to depend a lot on the prover's style. Yeah, Harry.
Harry Goldston, so I've done some work on automatic key automation.
Yeah. We looked at your paper.
Sonic relationship between the automated and the automated versions and like, do you know, like, what would that sound?
Absolutely. So great question. We looked, so for Harry's paper with Jessica Shee, Benjamin Pierce, and Andrew. Okay, yeah. Is about de-automating rock proofs. So you take these proofs that have automated tactics and you turn them into lists of longer, sort of more atomic tactics. And this is, would you like to answer this or should I keep going? Just want to give you floor time or air time. But,
Oh, okay, yeah. So like for this is more of like a live coding tool where it just like parses the proof, and then we personally like we just pick like the fixed nodes to the tactics. So I would say I don't think there's a relationship between like I don't think you would be able to see that relationship, right? 'Cause, I mean, we like is he asking like does auto sound similar to how we break it down?
Yes. So I think the way you break this down in the tool is you kind of get everything auto is doing, and then you just insert that back into the proof instead. Yeah.
Oh, okay.
So great question. No, it's okay. We'll answer quickly, which is that yes. So auto sounds like all the things that it is playing. So theoretically, yes, right? Auto at least does. And then semicolon is there's a certain amount of like how many goals is semicolon being applied to that is a future direction right now, because that actually turns out to be much harder with just the language server protocol. Really, if you wanted to make this easy, you would just fork the rock prover and do it in rock. But then you have to make OCaml MIDI, and you also have to fork and build the rock prover. So this is why it's a future direction.
All right, I think I solved our tech issue for the next talk. So we will once again thank the speakers. Thank you for rocking the room. You need to stay here
Yes, I will stay here.
because we are doing a demo next. We have a remote presentation, but because it's a remote demo, we need someone live and you're able to mess with the demo. So
I will say the audio thing here has been an issue. So I can play the sound for the demo off of my computer, but then I should not talk. Or actually, even this will pick up the sound itself. So I'm wondering if we should maybe take a minute to figure out this, because otherwise the whole demo is just going to echo like our table of contents.
the demo will echo like a table of contents. Sounds like
Brand new sentence. Yeah. So the demo has sound. We're going to present Dylan Davis's demo, which is a really cool kind of interactive audio experience. And Yeah, Dylan can tell you a bit about this from Zoom, I believe.
So let's go ahead and get started with Dylan's video.
Yeah.
I think that will probably work.
Yes.
And we'll see if this room can play audio from its own computer.
Yeah.
It can. However, it's very quiet.
Very quiet.
Does anyone know how to turn the volume up in this one in the room?
VLC also exists on desktops, you could try. VLC.
Can be more.
Well. Can I overdo?
Speakers, is it coming out of which what's the output currently?
It's the room.
Okay.
Well, if everything's at max.
Okay. Are there,
Everyone, Dylan will be slightly quiet. That's already
Yeah.
max.
are there other speakers in the room that would work better?
Not that we can get to on this computer.
Okay.
All right, everyone, if you can't hear Dylan, please raise your hand. We will defer this till after the break if we have to. It is going to just be a little quiet. All right, here we go. Yeah, unfortunately. We'll try to do it after the break. Unfortunately, it is too quiet to be understood. Every volume mixer is at max.
Yeah.
The room is at maximum. Here is the maximum.
Yeah. Would it be worth trying these speakers to see if they're louder?
They exist.
They don't exist.
But.
Or, well, first it helps to have the volume.
I don't think.
Oh yeah, they're totally inaudible too. All right. Yeah, we'll figure this out after the break.
With that, I think it's Jared's time.
Yeah.
Okay, this time I'm gonna log in. I'm gonna go to the Zoom.
Still might be version. What do you mean? It's I think the mic's on just.
Yeah.
It just means that the people who are listening to the recording.
All right. What's the accumulated wisdom on playing out of laptop speakers?
You can do it, turn your laptop sound on, but then don't talk. Slash, you might get feedback, unfortunately.
Oh, yeah.
Yeah.
Zoom audio. I need to. So we'll just put this to. Test. No, that's playing out the room. I need a. Wait, I know how to do this.
It sounded check before.
I know, but I'm in a Zoom meeting now, so it plays out the speakers and out the Zoom meeting.
Yes, sir. That is.
I'm just gonna put it to my earbuds, and then it will just play out my earbuds. Okay, so it's not echoing through Zoom anymore, which is great. Now, is there anyone on the stream? Are you on the stream?
There's a stream is being recorded, so that's what we use for videos.
Okay.
But I can on the stream if you need me to test something.
Yeah. I just want to play anything and
Right,
make sure
play
it
something.
makes a sound, and then we'll be good. For my sound as well. Yeah, this is good. This is good. I think everything will work. I predict everything will work. Okay.
Yeah.
Really?
Well, let me see.
Sorry, it's gonna keep going. I can't stop. So welcome to my toner demo. That sounds like a great intro to me. Let me make sure I am displaying to this thing though, which I need to do with this. No? How do I display to that? with the HDMI, my friend? HDMI. I think so. Oh, I need to share to the Zoom, and then that will play it there. Gotcha. And do I share? I don't share sound with Zoom. You're right.
You
Good.
do share sound in Zoom.
I don't want to, but it's working already without sharing sound.
We can hear it in the room.
Oh, but you can't hear it on Zoom.
Well, I don't know.
Oh, okay. I'll share the sound. All right. All right. Here we go.
Yes.
All right. Oh, brutal. He's near it. Yeah. Increase content. Entire screen.
Right.
Oh, lovely. All right. The show on
That intro one more time.
All right. Welcome to my demo. Can you hear it? No. Okay. Well, it is what it is, I guess.
Kurt tries to share it.
Yeah, let me share one more time.
Right, here's what we're gonna do instead. I'm not gonna do any of this stuff. You're going to put that microphone on your computer.
Oh, yes, just like last year. All right, and I turn this on. Yes. This worked so well. No, this worked great last year.
5.
Historically informed presentations. What we're calling this. Okay, I'm gonna try it one more time. Welcome to my demo. Obviously, that's playing out this organ here. This is a demo on my music composition language called ToneArt. ToneArt is abstract syntax for music scores. It's an embedded DSL in Racket. Big Racket fans in this audience, it seems. Awesome. Woo! So it's better that I play more music and do less talking. So we're going to start off with an excerpt from a Bach prelude or a Bach toccata and fugue. It's the toccata and fugue in D minor, but it's not that toccata and fugue in D minor. It's a different one, not the one everyone plays at Halloween. This is the Dorian toccata and fugue in D minor. Yes, Dorian, big Dorian fans as well. All right, so it's going to play out this organ here, and something you want to take note of is what keyboard it's playing on, because a big element of this piece is it swaps keyboards as it goes along. In organ parlance, we call these manuals, and this is manual 1, and this is manual 2, and this is manual 3. Watch manual 1 and 2. Okay, and we will play it. Oh, let me get the setup first. You off, and that should be fine. Okay. So that's the toccata and fugue in D minor, and you're probably wondering how I got it to the organ. It is actually using MIDI, like this group was talking about, but before it's using MIDI, it's using MuseScore. So this presentation is about my new front end for ToneArt, which is embedded into MuseScore. So if you were here at my demo last year, when I wanted to input something, I was painstakingly going through like from beat 0 to beat 2, there will be an A in the 4th octave. And from beat 2 to beat 4, there shall be a B in the 5th octave, which was a huge pain in the butt. But now we can just paste the score in a MuseScore, and obviously that scales way better. Look at how long it would take to import these note by or input these note by note. So I had to make some administrative tweaks and things, but it's really cool. The coolest thing is these custom text fields here. This is my DSL in these performance directions. This is tone art code, and this is the only thing that matters. What I'm doing is I'm specifying which manual these parts should be played on. Now, MuseScore can play notes just fine. That's funny. But it doesn't know anything about pipe organs, like many of us in the room. And so it probably, I assume. And so I have to actually interpret this using tone art, which is why it's cool that I can just embed tone art right in here. So you'll see some of the constructs we saw. That part where we're swapping manuals is right here, 2, 1, 2, 1, blah, blah, blah. And that part where we were doing the hands thing, we were like, do, 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 do. You can see kind of like it kind of swaps, and then the other hand swaps, and then this hand and this one. So that's pretty cool. But what's super cool is it's not like free text and then we're like running eval and then we're like, we have like a fixed language. It's using the Racket module system because we're embedded in Racket. So we're actually getting these manual forms from the module toneart/organ. That's our organ standard library. If I didn't import this, this would have no meaning. There would be no such thing as a manual to say, what is a manual? Because we're trying to be modular here. We're doing our best. So that's cool. And then, of course, the flip side of require, if you're familiar with Racket, these are bog standard Racket module statements. It's import, export in Racket. The flip side of require is provide. And we're going to provide out this theme, which we've named here. We've named this whole theme, this whole score, BOC-D, and we provide it out here. Yeah. And just a brief aside on what set is. If I didn't put set here, it would name this note BOC-D, which is especially egregious because it's not even a D, it's an A. So by putting set here, it says take from the beginning and go all the way to the closest reset, which is at the end, cleverly. And now we get the whole score all at once. That's great. Let me provide it out. So that's how I played that. But you're probably wondering like exactly how. Like this is a cool front end, but like how did I get it into Racket? So the way I did that was I exported it to music XML. And music XML is like a music interchange format that's much easier to parse than MuseScore's and binary files. And it's more standard. So other score editors can use it. And so let me show you what the music XML looks like, because that could be helpful for someone who wants to replicate what I've done in some other language. So blah, 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 lots of cruft. Oh, it was in here. Lots of cruft, but you'll find that we've got all these note forms. That's a native music XML construct, notes, and we just parse them out with a music XML parser. And then for the custom stuff, we use performance directions. So that text comes through as directions, which are performance directions. And you'll see that our text is right here, and we can parse that right out and treat it. We can treat it as tone art, roughly using eval, but it's not eval because it's Racket. We would never. And you can see our sets up here as well, the set. And the last thing, and the thing that I think I'm most proud of probably, is the credit field. So this kind of opened my mind a bit on what the meaning of requiring a module is. Because what is a module dependency but giving credit to the programs that made your program possible? So you can see that the text for the requires is in here and the provides is in here. And if anyone else wants to try this embedding in a different language and using some preprocessor stuff, I'd really love to see that. You know, if you do it in Python, you could probably be very popular and have lots of money, unlike me. But yeah, I encourage you to. Please credit me. So yes, that is how we get this in. And we just have a little stub here that points to the music XML right here. Sorry, right here. And that is how we load it into Racket. So that's cool, but at the same time, it's kind of boring. Why is it boring? Because we just took the whole score and like dumped it in. And ToneArt claims to give you composable composition. Like the idea is when you make a module, you put like lots of different themes in there, like the materials you want to compose with, not just the whole score. And then someone else can take your module and use your themes in their own composition. So let me show you a more sophisticated one, only slightly more sophisticated. This one has multiple bindings that it exports. And the premise here is we've taken a couple themes from the D minor prelude and fugue and we've broken them out and then given them their own independent names. So you see here, this first one's called, it's the da-da-da-da-da-da-dee-da-dum, that part where the hands were going like this. And it's called bounce. Let me play it for you, in case you forgot about it. That one. It's called, and I call it bounce because I think it's kind of bouncy and cool. I agree. And then we reset, which means we grab this as this name, and then we set the main theme, and we get the main theme from the beginning, which is the that opened it, that fiery opening. And you see we provide two names out of the module system. So that's cool. I have one more quick score for you. This is just kind of out of obligation. This is the source that was I presented in the demo proposal that I submitted to be able to give this talk. I felt obligated to show it to you. It does actually run. It was not a spook. And the two we want to look at here are the theme one, which is theme one, and then down here we have a different thing here. It's called a registration pattern. And I don't know if you've guessed by now, but I'm here to present my music language, but I'm also here to evangelize for the pipe organ, which I love. And so this is actually, all the things you've seen so far have been notes, but this is not notes. This is something different. This is pipe organ registration, which is to say it's these tabs here that I push and unpush. So if I take all these off, you see they're all off, and I press this keyboard, nothing comes out, but I can turn them on, and you can hear it's different sound. So that is what we call registration in the biz, and you can turn them on, and then you can turn them all back off. Whoops. So that's what we're talking about here. And what this says is on manual one, the bottom manual, put one flute. It's we call it a thin registration. It's very light, quiet. Put one flute on the bottom manual. Put one high string on the second manual, manual 2, and put the oboe on the third manual, which is a bit louder than the other ones. And then what these are saying, it's just like in the Toccata fugue. It's saying start with your right hand here on manual 1 and your left hand here on manual 2, and we'll do da 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 dee da. And then for the last two notes, you shift this one up to manual 3, and it'll play out the oboe. Bum 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 bum, that kind of sound. So I'll play that for you later. Just trust me on this one. It's pretty cool. So yeah. So that's kind of our concept of like a module, and you make multiple bindings and you provide them all out, and someone can like use your materials in their own way to make their own score. And so I'm gonna quickly play that for you now, because it wouldn't be a ToneArt demo without live coding in the REPL dangerously. So first off, we need to require the ToneArt modules. So we're going to use Racket module system statements. So we're going to require the decomposed Toccata here, which is, if you remember, the one with the bounce theme and the main theme. And we're going to require the proposal was the mandatory one. And because we're just integrating with the Racket module system, we can do really cool things like rename bindings and give every binding we import a prefix, which like show me an embedded DSL that's doing that. Like really, it's really cool. It's a detail, but it's an important detail. So down here, can everyone see down here? I hope so. Down here, we're going to do a little, this means send to the back end. So we're going to send a score to the back end to be played. And we're going to do talk : that's the prefix, and then we'll do bounce. And we'll do it as tones, so it'll sound like a little synthesizer-y thing. And then they import a little slow, so I increase the tempo. Okay, and then we'll run it. And sure, and then we can try out the one from the demo proposal, the one from here. Okay. And of course, you want to hear that reg pattern thing I was telling you about, the registration thing. So I'll show it to you, colon reg pattern. And that will have note to MIDI, because tone, it doesn't make sense for tones. Tones don't have keyboards, but the MIDI we're sending, it's going to the organ, so it knows what to do. So if we do this, and I'm going to try and quickly slide over to the organ to show you, see how this is our current registration? It's going to set the registration and then start playing it. Okay. So let's see, and then pop over. There's the O at the end that I promised. And so that's pretty fun. You can mix and match these themes. But I think the real point of this, like the real fun of this whole thing, is I can take something from different modules and combine it together. And so what I'm going to do here is take the bounce theme from Bach. So this is a 300-year-old theme that is now transcribed in Tonart. And this is something I wrote randomly at 2 a.m. 3 months ago to try and get a paper submission in time. And when you combine them together, you get something that's pretty cool, despite them being so different. So let's do this, and then we'll swap over the organ part. It plays like oboe. It's the same concept, but in a Bach piece. So I think that's pretty fun. Yeah. I have more, but how are we doing on time?
After that session, also that's
Oh my gosh. Okay. Do you want to see something crazy? Yeah? Okay. Okay. I don't know. Yeah, this is already too crazy. Stop, please stop. Rewind, pause. Okay. Well, since we have the time, I want to show you that Tonart has a logo now. Yeah, okay. And there's something kind of special about this logo. Tonart actually is a family of logos because the logo is context sensitive. Let me explain. You can see up here that the presentation is in the key of C# minor. Just roll with it. Yeah, C# minor. Now, if I hit this, I have a button that changes the key. And as you see, the presentation changes key. And so does the logo. And that's not the only thing that it's context sensitive to. So you remember our bounce theme, right? The da 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 da. You're probably tired of that by now. You've heard it so many times. Well, you're about to hear it about 5 or 6 more times. What Bach is doing there in that section is he's making a cycle. Da 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 da, and it just keeps going, and it could go for eternity. It's an embedding of an eternal loop inside of like a finite, like seemingly finite music. And he's doing that by changing the mode. So what I'm going to do is I'm going to try and replicate it in my little GUI tool here. And you can see the mode up here. It's currently Aeolian. And even if you don't know modes, you know when text changes from one thing to another. So, and observe the logo as we go through this process. Oh, I hope I don't mess it up. All right. Let's get the organ set up for it. There's a button to do that. All right. So, ready? Are we ready? Okay, let's do it. Oh, it's a lambda clef. It's not a G.
Exactly.
It's not a G clef. Yeah. So let's do it. Sorry, what's next? Submitting what's next? What's up? Of course, but Bach doesn't do it, but I do it. I'll show you. What's next? Next is medium, and this is where Bach stops. But we have a first page, so we're gonna keep going. We're gonna push right into low Korean. And then Phrygian is the last one. We started at Aeolian. Thank you. And there's one last thing it's context sensitive to. This is just silly, but there's a transformation called inversion in music for all the theory geeks out there. And so I'm gonna apply inversion to this. And now the logos are down. And this, you can actually find this in Bach music. He'll draw the clef upside down when he writes a canon in inversion. So it's not unprecedented, but it is wild. And you can hear that our bounce theme is now upside down. So the best way to hear this sound is ba-dee-da-dee, because before it went dee-da-dee-dum. So you can hear it's the other way at the end there. Okay, now my last thing, I promise, is I have a puzzle for you all. And your submission can come in whenever, wherever. Feel free to watch the stream back, to listen again, or do whatever you need to do. But what I'm going to do is I'm going to play two themes at the same time. These are both themes that I've used in either of my farm talks. And if you can tell me what the themes are and where I introduced them, I'll give you a prize. So, but the trick is it's a little bit encrypted because we've inverted it and changed the mode. So I'm not making it easy on you. I'm also going to play out the synth so that it's really hard to parse the voices apart. So ready? Here we go. All right, best of luck to you. That's all I've got. Any questions? Do we have time or? Okay. Yeah.
Did you consider using the hero device system to tell you about your photo?
Oh, I was thinking about that right away. Remember you said red and blue is considered a faux pas, and I'm like, no, he's gonna hate my presentation. What's that? Oh, yeah, something verified. You have a question?
Yeah, so
it seems
like the annotations in the source,
yeah,
right? It seems like that can be arbitrary bracket code. Is that correct?
It's tone art code, but more or less, yeah, because the tone art code could be racket then racket code. Like,
okay.
So yes, it's arbitrary racket. Let's go with that.
So have you found any use cases for putting things other than just the kind of names of things in there?
Absolutely. I've run slideshows on a timer with I've put like slideshow code in there and then run a slideshow using a music score. Stuff like that. It's pretty fun. Yes.
That was a great talk. I really enjoyed it. And
Oh,
for
good.
a theory geek, it was also really fun.
Oh, good. I was hoping I was targeting.
I wasn't expecting this coming to the conference.
Yeah. What's your name, by the way, and where are you from? I forgot.
Sorry?
What's your name? Where are you from?
I'm Tiana, University of Washington. But I grew up in Serbia. I went to music school there. My mom was a professor, so I got to listen to about this stuff my whole life. The only thing that irks me is that violin key there, because it doesn't match up.
Oh, you don't like the G? You don't like the yeah.
Because it doesn't. This is the what's the other in English? The name of the other key. Bass key.
Bass button?
Yeah, it's the I don't know the music terminology in English, but they don't match up the key.
Yeah. Graphic design is not my passion. There's much to be improved. I tried really hard to get them to go in the right spot, but they kind of shift around when you add too many sharps.
That's a very mind freak, no pun intended.
Yeah.
But
no, you're intended.
But it's just it looks improper in this.
Yeah. Sorry. Visually dark. I totally understand. Yeah.
Everything else was great.
Yeah. That's the hard part about music stuff is you have to get all the drawing precisely right, and it's the hardest thing, which is why I think May recommended I use Lily Pond. Which would be smart. Yeah. Oh,
Oh, yeah, I love the, like, yeah, store text as a way to program code. I mean, there's a fair amount of flexibility in how that can be laid out. So how do you go about associating it with specific points of time? Is that
Yeah.
sort of music XML? Or...
Yeah, sure. It is part of the Music XML. Music XML is a little frustrating to parse, I won't lie. But yes, it is actually, it's organized into measures, and then each measure has notes, and you can try and parse out that stuff. The set thing is actually part of a struggle I was having where it's like, if you put a notation, there's an ambiguity. Does it apply directly to the note it's on, or does it apply to the rest of the score? And there's no way to solve that as far as I can tell without like encoding those rules specifically in like a predefined table. So yeah, good question.
Just about at the end. So as we think this is your last week. This is the end of our morning session. Until the first stop of the afternoon session. If you are an afternoon presenter, that means that you should find me because we have to shift all of the afternoon blocks a bit. We did have 22 spare minutes in the afternoon, so it's perfect. No issue there. Thank you all. We have a coffee break now about health codes where you saw registration. We'll be reconvening here in 30 minutes for our second session. If you are a second session presenter, find me during the coffee break or come up right now. We would love to do a sound check for obvious reasons.
I'm gonna be tricky, May. I'm sorry. I
I assume you need sound.
I do, and I need sound from PD.
Computer.
Yeah.
Okay.
So I thought like.
All right, everyone. Just about ready to start. Still have a few people getting drinks, but I think it is not worth waiting for them, if that's all right with you.
I think I'm hearing it. Now everything is echoing. I don't know. Oh, you know what? If I go, no, my audio is off.
Your audio to Zoom.
Okay, and that's going to Zoom now?
Well, presumably. Let me get my laptop.
Presumably.
Presumably.
Okay, presumably. Oh, that's a sound. Testing. Are you still? Okay.
Click another button and then we'll be able to test.
Pas de problème.
Recording in progress.
Okay, can you hear me? All right. Okay, good stuff. It's the system here has been too complicated to do straightforward audio that will get recorded and everything else. So sorry. So I will do my best to have the audio come through the room first, and that's the only thing we'll care about today. My name is Carrie Hagan. I'm a professor at the University of Illinois, Urbana-Champaign, and my specialty there is composition theory, but specifically computer music there. And some of you may know that it has a long history of computer music. So I don't know exactly how to pitch this talk. My impression is a lot of you are very technical and very mathematical, so this might actually be somewhat remedial. And then it turns out that it's the weird music that I have to explain. So I'm going to do my best to talk down to absolutely everybody. So I'm going to first talk about a little bit about where I come from musically, because it's not what you're expecting, I don't think. And then I'm going to briefly explain cellular automata, which is probably going to be beneath you all. And then I'm going to talk briefly about what one-bit synthesis is and the kinds of music that people have done with bit-crushed audio. Bit crushing meaning low bit depth audio. And then I am going to show you the patch, the pure data patch that makes the audio for the piece that you'll hear tonight if you go to the concert. So hang on, here we go. So to explain my musical approach, I practice what I call textural composition, which means you will not hear harmony, you will not hear melody, you will hear sound, you'll hear sound wall, and more importantly, even in electronic music terms, I don't even employ electronic gestures. It's sound mass, full noise, full in your face. Just warning you now, you couldn't represent what I do with MIDI, and we saw a lot of MIDI in the beginning of this day, so I just want to put it out there that we're not going to see any MIDI in this particular talk. So what is cellular automata? Well, if this is going too slow, stop me and I will just go right to the music. But the idea is that cellular automata are made up of cells and they have states. In the simplest example, the state is 1 or 0, alive or dead. And the most famous is two-dimensional cellular automata, which, if this works right, I can just do this. This is the famous Game of Life by Conway, and it has emergent behaviors. There's simple rules. You know, a cell is alive based on the number of cells alive around it. It dies, it's born, and so on. All the metaphor of living in a population. And what's really cool is with very simple rules, you can get complex emergent behaviors. And complex emergent behaviors are great for generating timbres. So instead of using two-dimensional CA, I use even more basic one-dimensional elementary CA. I am going through this really fast. To tell me if this is, like I said, I suspect I'm talking to much more technical people than I usually do in my day-to-day life, so I will slow down if I have to. But to remind you about elementary cellular automata, it's defined right to left. If you take 3 cells to find out what the middle cell is going to do in the next iteration, there's, of course, 8 possibilities with 3 cells. So you start from the right to left, 0, 0, 0, 0, 0, 1, 0, and 1, 0, and so on, count up in binary. And then what the cell becomes is determined by the combination of cells, the number of cells alive. And so then you put the result in a row like this and read it in decimal, and that becomes the rule number. Anything that can be represented by a 1 or a 0 has only one bit of information. And I'm foreshadowing the rest of my talk there. I don't normally point people to Wikipedia, but I feel fairly confident that Wikipedia is good at elementary CA. And this is an example from their page. Now it is two-dimensional here, but that's because each row of pixels is the next iteration of the one-dimensional CA. And you can see here in emergent behavior, this starts with one cell alive in the middle of the one-dimensional array, and with each iteration it grows. You can see that there's repeating patterns followed by fractal patterns. A lot of cellular automata look a lot like the Sierpinski triangles, and then they do other things. And I will tell you how I implement this into sound after I tell you a little bit about one-bit synthesis. Are we cool with CA? I think all of you probably know more about it than I do, so I'm just gonna stop there. So what is one-bit synthesis? Well, it comes as a result of the way you have to encode analog audio in the digital domain. As you know, computers have finite number of numbers, and analog is an infinite number of infinite numbers, right? So the computer first has to make the time domain discrete, and we call that sampling. And then you have to make the amplitude discrete, and we call that quantizing. And so obviously the quality of audio is going to improve when you have more quantization levels, and what determines the quantization levels is the number of bits that can represent that level. So standard CD quality for us old timers is 16-bit. So that's 65,536 levels. That's often, but depending on whether you're looking at line level or mic level, about 5 volts. So you can split it up. Current recording quality is at 24 bits. It's been a morning. So at 24 bits, that's over 16, almost 17 million levels. So you can see with a fairly small number of bits, we can get some pretty decent audio. But there's people who are into retro, and there are people who like the kind of correlated distortion that happens when you do something called bit crushing, which is you take some sort of signal with a high bit depth and you reduce it to low bit depth. Now the retro people like it because the old gaming consoles were 8-bit audio, and there are people who spend a lot of time trying to get familiar sounds recreated in 8-bit, which is not easy. And here is a sample of some 8-bit music. It's an hour-long collection of multiple tunes by Technoax and Kevin MacLeod. You recognize the gaming console kind of timbres there. And the challenge here is, how do you get noisy things like drums to be presentable in 8-bit? So unlike me, people who do a lot of these 8-bit kind of things are actually trying to emulate traditional music parameters and timbres. So what's happening? Well, let's say, for example, we take that sine wave and we quantize it at 2 bits. You can see that it introduces discontinuities in the signal, and when you introduce discontinuities, you are creating correlated higher frequencies in the spectrum. So that's what bit crushing does, is it gives a distortion that's correlated to the original tone. But what happens when you quantize to 1 bit? That's it. You're left with a 0 or a 1, which means that all you can do is a single pulse to a rectangular wave of any duty cycle. You can do white noise too. It turns out, it's a little counterintuitive, but it turns out if you flip that coin between 0 and 1, uniform random distribution, you'll get white noise out of 1-bit synthesis. All right. One of the famous examples of 1-bit synthesis is the 1-bit symphony by Tristan Parrish. This is more like an artifact than something in audio. He packaged a single digital chip in a CD case. You can flip the audio on, plug in your speakers, and then you can hear 1-bit music. And again, I'm going to play this, and it's not going to be anything like the 8-bit chiptunes, but you can hear he is still trying to work within pretty conventional musical parameters of rhythm and pitch and timbre. So, the challenge these folks are doing, or the challenge that they're taking on, is how do we make really low-bit audio sound like real musical instruments in real music? And I'm more of a kind of like, we can do anything with ones and zeros. Why don't we find out what 1-bit synthesis can do, as opposed to trying to force it into doing something that other things do much better? And I didn't even know I was doing 1-bit synthesis. Technically, I just didn't cop onto it. What happened was I'd been doing a couple of things that worked with just raw ones and zeros, and then I had a student who was doing a senior project with me who brought in all these papers and music by people who did 1-bit synthesis, and I realized, oh, yeah, okay, that's what I'm doing. So how this works is going back to this picture of the cellular automata. I am creating a wave table. So again, this is where I don't know where I'm pitching this. A wave table and wavetable lookup synthesis is supposed to be one cycle of a waveform, and then basically your software reads that wavetable in a loop at the frequency you set it to. So I'm using the cellular automata to populate a wavetable. So it can have very high frequencies because you can have more than one square wave in the wavetable, but the wavetable is reading it as if it's just one waveform, which is cool because then you can also get cool aliasing things and frequency foldover. And that's cool to me because I like to be surprised by my processes. Not cool to most people who want to have ultimate control over everything, but that's essentially what I'm doing. Is I'm filling a wavetable with each iteration, with each cycle of that wavetable lookup. I'm repopulating the wavetable with the next iteration of the CA, and that creates interesting timbre patterns. And so I thought, because it makes more sense to hear it than to let me do this again. It makes more sense to hear it than to just have me describe it. I just thought I would show you in Pure Data. Does everybody know what Pure Data is? No. So Pure Data is a music programming environment that was created by Miller Puckett. Same guy who created Max, except Max was taken over by a company called Cycling 74. But Pure Data is open source, so it's uglier. And it basically, we talk about programming languages and native languages. And Pure Data was started in 95, 6, 7, around there. And I went to UC San Diego in '97 and became Miller's research assistant. So like I've grown up with PD and it's grown up with me. So this patch here, it looks messy. It is messy, but it's the way I've generated my sounds. And I have some windows here. This is my wavetable. I originally made this patch to be performable live. And so I've used it in the trio I have with Miller and with John Bowers, who is a sound artist, performer, circuit bender, crazy guy in the UK. And the problem with one-bit synthesis is that trying to layer two sounds together in the same track doesn't work, right? Normally you just add audio signals, but if you have one bit, you add two 1-bits together, you still just have 1 bit. So some of the research out there is how best to layer things. Do you use an AND gate? So only when they're both 1, you send out a 1, or an OR gate, or an XOR gate. It turns out that all 3 of those options are good for 3 different cases. And so you can't kind of change those cases on the fly very easily. So as a live performance patch, I can only make 1 sound at a time. But I wanted to make a lot of sounds at a time, so I recorded a whole bunch of output and then put it together in a DAW and then sent all the audio to different channels. So what you'll hear tonight if you come to the concert is a 4-channel version of a kind of fixed medium version of these sounds. I've already warned you about what kind of sounds come out of this, so I'm just going to play some of them. Look how pretty that looks. It sounds even better. Now, in that particular example, what I've done is I've seeded the CA with random 1s and 0s. So every time I click this button, it's going to have a slightly different timbre. Which is nice because then you can get some interesting results when you're playing it live, unexpected results. So I'm just gonna, I'll just click a few of these so you can hear the kinds of sounds that will come out tonight. And you can see the pattern, you know, when we saw that Rule 30 pattern, how the repeated functions kind of moved over to the side and then sort of fractal stuff happened in the others. Well, I have Rule 30 somewhere here. You found it. There it is with the single cell init pattern. So this is exactly what that picture in my presentation was. So you can see why something that evolves like that and creates full in-your-face sound would be something that a sound mask composer, a textual composition composer would be enamored with. And so, I'll play a few more of these. And I'm realizing that I've gone over time, so I am just going to stop there, just because that shows you just a couple of the emergent behaviors and the kinds of timbres that come out of it. Sorry, I went over.
No worries, we started a little late. Let's think about it.
Oh, sorry. Thank you.
While the next talk is wrapping up, let's go ahead and ask a couple of questions if you have any. Claire, what's the oh shit button?
That just turns everything off in case something blows up. It's just good programming practice to have a no shit button in every patch you make, especially if you have feedback and stuff like that. Yeah.
It's amazing. I love it because I love this kind of research. Just one question. Why conceptually is write 1 bit go from 0 to 1? Electrically, if it is not, if you have not the negative side of the waveform, the speakers tends to
I think related, I was curious if the choices of wavetable length or playback frequency or that sort of thing have particular effects.
Massive
Yeah.
effects.
How do
So,
manage that?
right. So, I use a wavetable of the power of 2, and that's probably not important for this particular use. But it's habit, because often I'm using 4-point interpolation in wavetable lookups, and you need a power of 2 plus 3 points to do that. That's just habit. But then in terms of playing back, you can specify the frequency. So if you do like a sub audio frequency, like 10 hertz, then all those individual pulses and square waves inside that wavetable will be heard at a normal frequency. And the patterns end up being more rhythmic than pitch or timbre, right? But if you do it at higher frequencies, you get the cool fold over. Are you guys ready to go? I don't want to.
Yeah.
Okay, then I will.
But
Thank you for your questions.
Thanks, Carrie.
yeah.
Moi, je fais un zoom deal share screen.
Share sound. Is there anything else that I need to do?
Nope.
That's it.
Just share, yeah.
Let's make sure the audio is coming out of this computer.
Yes. No, not this on Zoom. Okay.
I think you're okay. Assuming the live stream is working.
Editing community. Let's go in and do.
Thank you.
Okay.
Okay. One second. So if anyone wants to talk to the discussion, I can redirect it to tomorrow's workshop. Technical issues. I know. So what? These are more.
Yep. Hi. So in 1961, the avant-garde composer and philosopher Henry Flint proposed concept art, which was art where the material is concepts and not in the same way that, for instance, music has sound as its medium. And he was inspired in this by what he called structure art. This is stuff like fugues, total serial music, a lot of music where the intended purpose is to convey some kind of structure, and simultaneously by mathematics, but going beyond structure art, which he didn't like the structures, and he also didn't like it as music, and going beyond mathematics because he didn't like the idea of discovering theorems. He was a very out there philosopher. There's what I would say some real examples of this arising from mathematics, going beyond discovering truth, and this would be the paradoxes of formal systems. The intention of something like naive set theory is to capture truth or, naive dependent type theory, but they're subject to inconsistencies that are beautiful and rigorous concepts, but you can't consider them true because they destroy the system that they were intended to use as their notion of truth. So my goal with this is to create structure music inspired by the structures of these genuinely beautiful pieces of concept art. My aesthetic influences on this are Yannis Xenakis, less on the actual sounds of this, unlike the previous one, and more on the approach to developing this. He used a lot of mathematics in his composition, and I thought that was an interesting method. And he emphasized that not only should it have mathematical structure, it should have arbitrary choice as an element of the art. I'm also inspired by Catherine C. Hennicks, who was a composer, mathematician, and philosopher. She worked with a lot of relevant figures, including Henry Flint, Lamonte Young, the minimalist composer, Pandit Prannath, the Indian classical musician. She taught logic at MIT. She worked with the Russian ultra-finitist, Alexander Asenin-Volpin. Very interesting figure. Her work, The Electric Harpsichord, is one of my favorite pieces. And then in terms of some of the actual music in this, I'm inspired to some extent by techno, metal, jazz, and I'll talk more about that a little later. So Girard's paradox is defined in dependent type theory, and it's a form of the lambda calculus where types are allowed to depend not only on types, but also on terms. It basically eliminates the split between terms and types. There's a judgment of this term has this type, and types are simply the kinds of terms that can be the type assigned in that judgment. You don't need to understand all of these rules, but that's generally how that works. Girard's paradox appears in certain basically naive forms of dependent type theory. It's a variant on the Burali-Forti paradox of ordinals. Basically, it says that if you have a set of all ordinals, there's an ordinal corresponding to this set, and then that ordinal has to precede itself, which is impossible by the definition of ordinals. And the problematic feature of the type theory here is what's called type and type. If you look at this rule here, the type star is the type of types, and that is assigned itself as its own type. That's not consistent. Real type theories resolve this by using a stratified universe levels generally. when it doesn't have it, you get the paradox. It was developed by Girard using this theory of orders without torsion, extended by Thierry-Coquand to system U-, which is a simpler version of it. And the proof term was simplified by Antonius J. Herkins. It's based on this notion of what he calls a powerful universe. You encode the power set of a type as the predicates on that type, and then a certain type in that is in a certain way isomorphic to the power set of its power set. This gets you the paradox. I'm doing this with a system that I call soundproof that I've developed for the purpose. My goal is really only to translate this one term, but to be principled about it, I developed a system for translating arbitrary terms, which is easier really than trying to get each piece of the structure manually. So it translates a term from lambda pi, which is a tutorial implementation of dependently typed lambda calculus by Loch McBride and Sfirstra. It's bidirectionally typed De Bruijn indices. It's got type and type, and all of these are features that are intended to make it simpler to implement, and that means that it has Girard's paradox. I translate that into what I call a sound tree, and I'll discuss that going forward. And then it's turned into sound using the Rust library FunDSP, which is a library of composable combinators for digital signal processing pipelines. And the connectivity of these pipelines is checked at compile time. It uses basically compile time natural numbers, and the resolution of this ensures that it's all going to work and you don't have any dangling loose ends. So the big question is, if we're going to translate it into a sound tree, what exactly is the tree structure of a proof? So there's the natural deduction style, and that's a classic one, but we have the type theory proof term, so we don't really need that. It's unnecessary, but the visual layout is interesting and comes in later. The term structure, we just have the abstract syntax tree of the term. The problem with that is that when you get to a variable, bound variable 0, in this example, what exactly does that variable signify? That's really not clear. The importance of a variable depends on the specific type of the variable. So instead, we use the call tree of the type checker. Basically, I re-implemented the type checker and had it build up a sound tree as it checks and infers the type. And then this contains the full AST structure, because every term you have to check all of the types of the subterms to verify that it's valid. And for most terms, it just stops there. Once you know the types of all the subterms, the type of the term is obvious. But when you include variables, you have to verify that the type is valid, pulling that from the context. It's not in the AST, and so that adds that into the call tree of the type checker. This gets you a richer musical structure and better conveys the significance of things. So this is an example of some of the code from the type checker. You can see it at the top. It gets a tree and a type from inferring the type of the function being applied, verifies that that function is a pi type, that's the dependent function type, checks that the argument has the appropriate parameter type, and gets a tree out of that. And then it returns a combination of the result type of the application and a sound tree, which has the melody for the application node, and which also plays the trees for the functions and the argument. So the idea is that for a sound tree, each node variant in the AST is associated with a particular little sound. In this case, it's a melody, basically. And what we do is simultaneously, we give a duration to the root, we play that melody over that duration, and then the sound tree splits up that same duration among its children so that, and then plays the first child over the first portion of it, the second child over the second portion, and so on, and does this recursively so that you get the whole depth of it. And as things go deeper in the tree, we pitch them up. And if this is a spectrograph of the result for a fairly simple one, you can see it's got these sort of spiky structures, and the durations are longer as it's at the lower level. That corresponds to the structure of the sound tree. And here's an example. So here, this is the type theoretic power set. It annotates on the left here a lambda. The lambda has a body, which is the pi type arrow type, or t arrow type. T is the free variable. The free variable has type, and the output of this is also type. And then we annotate the whole thing with type arrow type, which is the pi type here on the right. Oh, I guess this would be an easier one to gesture to. And we synthesize this using FunDSP. This is an example of a FunDSP pipeline. And I'm just going to skim over this because I want to make sure I have time. So here's a little bit more complicated of a term. This is the powerful universe U, and it is being covered up by the meeting controls. If I can hide these. There we go. So here, for all x of type, that's the t here and the pi. It's a function which takes the power set of the power set of x and returns, or sorry, a function from the power set of x to x and returns an element of the power set of the power set of x, which is a type.
The parentheses there are not balanced.
Yes, they are. There's.
Oh, so they are.
Yes. Okay. And so there are several points of choice in this. The important ones, first, the division of time between the children of a particular node. If we do it evenly, so that something with two children just splits it in half, this results in some really, really uneven sounds. For instance, in the paradox, we annotate that with the type false. If we did it evenly, half the time would be spent on the paradox, the whole thing of it, and the other half would be spent just on the type false, which is not a very interesting piece of music. If we divide it up based on size, if we do that raw, that ends up being too vague. Like, one of the key things that distinguishes between things at different levels, in addition to pitch, is how fast they're going. And if it's divided up purely based on size, all of the leaf nodes are playing at exactly the same speed. That doesn't work. So what we do is we weight with a fractional power, and we take the sum of the weights of all the children, and that to a fractional power. This compounds as it goes down, but then generally speaking, larger nodes will take longer, but it's relatively more balanced. We also, depth scaling, we use discrete octaves. It's basically the square root, because the depth can go up to like in the 20s, and we can't span 20 octaves. Square root divided by 2.5. And we also adjust the time characteristics of the note as we go up in the tree, basically changing the attack and decay so that it's got a little more of a twinkly sound as it gets deeper in the tree. But the most important question is, what sounds do we use for each node type? So first, the way that I had it set up was a sound generator it was just using melodies associated with each tag. I extended this using a trait sound generator that basically signified anything that we could sequence out over an arbitrary duration. So audio clips with some stretching, this ran into issues because it just takes a really long time to stretch audio relative to any of this other stuff. I did some stuff with loops, stochastic musical textures. Those ran into some difficulties. It doesn't change speed very much. That's something that could be worked on potentially in future things, but I decided to ultimately use still basically melodies, but with more variance in rhythm and post-processing effects and so on. And one of the key things that I wanted to do with this was be able to experiment with a lot of different ways of presenting this. So I defined a trait called selector, which is basically a selector is a method of picking a sound for each AST variant. It can generate a sound tree for a term, but it also can have internal state, which it updates with each term that it sees as it goes through the type checker. So the idea is potentially the sound for a particular node in the tree can depend not just on that node itself, but on the sequence of parents that the selector saw as it went down the tree there. So there's a variety of these that I defined, but what I ended up doing was having the sequence of notes is determined by the AST variant of the node, but the variant of the parent of the node determines the rhythm, the synth instrument that it's using, and the post-processing effects that are put onto it. So it conveys both the specific node that it's at, but also what context it's in. So if you have a star that appears in the context of a pi type, that'll sound different than a star that's appearing in the context of a lambda, for instance. And here's an example of a bit more complicated of one. And you can see in green, I've highlighted the previous one, that's the powerful universe U, which is also that's this whole thing. And here it appears, you can see several times. So this presents the visuals of it. And here's a spectrogram of this. What of this looks like. Sorry. One of the other questions is basically for the terms, should we normalize them or should we continue to have like annotations and unapplied applications and so on? So this is one that still has the non-normalized formula. And you'll see that it gets quite complicated when you get to the details. Okay. Future work for this, I'd like to incorporate the reduction behavior of the proof term. It doesn't normalize, so I would have to switch it to a small step evaluator, which is kind of tricky with the bidirectional typing, and I'm not sure how I would lay it out with respect to time. And I'd also like to experiment with some more stochastic textures and so on. Questions? Do I have time for questions?
Part of this get set up.
Yep.
This unfortunately is you Everyone has a question. Ask the audience.
Probably a bit out of left field, but what are your thoughts on applying this type of methodology or some variation to listen to the SMP lib solve?
Well, I think you could try that. I think you would need to do something more complicated than lambda.py for that. And that is pretty far future work, I would say. But I think it could be interesting.
Some elaboration.
Okay. Yes?
Clearly, the complexity makes the sound interesting. We've mentioned before, maybe bad proofs sound worse than good proofs. Do you find that paradoxes sound different than sensible proofs?
I have no idea, but I think the method of this would generally produce relatively similar sounds no matter what proofs you put into it. This is intended as a way to produce a piece of music based on one particular proof. So I didn't put any real effort into making it sound different for different proofs. Yes?
Thank you for the talk. Under the sort of higher sonic structure of the full term, there's a persistent tone. What is that being generated?
Probably the annotation, which runs for the whole duration of it. And so if you have the melody that plays over the entire, the full one is like 40 minutes.
Yep.
If you have a melody that's playing for the entire 40 minutes, it's just going to sound like a drone at any particular moment of that. And it's a 4-note melody.
Yeah. I listened to the 40-minute version while programming rock and roll. And that undertone was something I was really curious about, because you could sort of parse out the melody with respect to the terms maybe a little bit. Maybe I was making it up, but that under thing is something else. Yeah.
For those who have set conflicts, can you tell Spray to find the full 40-minute thing?
Oh, yes. It is at isdra.bandcamp.com. Free download.
Nice.
You can ask afterwards.
Yes.
1 second. I have one teacher's prerogative to ask you a question.
Yes.
The underlying melody that Roger was referring to, extended over time, has sort of echoes of the Cantus Firmus tradition and Renaissance era polyphony. Is this something you're familiar with?
No.
Okay, I shall take my music theory questions offline. And I think, Ricardo, are you all set, or do we have? Looks like another moment. There was one question.
So there was this subtree that appeared in multiple places in the big proof tree. Is this recognizable by ear? Do you feel like a theme that repeats or?
The audio will go.
Sorry, I think I missed the start of your question.
Yes,
I was...
the green subtree that appeared in multiple places.
Oh, the
farm schedule.
Okay.
So if we
okay.
start in the next
That's
minute,
maybe
we will be totally fine to end on time. I do apologize that it means that our transitions are a little bit more boring than usual. That's part of the cost of
maybe
negotiations. There's a question, yeah. Okay, you see what joke popped in my head instantly, but I cannot share. But you can ask me.
Okay, so this is a record.
Sounds good.
And what?
Anyone know any good math jokes?
Three logicians walk into a bar and the bartender says, we should all have a beer. And the first goes, I don't know. The second goes, I don't know. And the third one goes, yes.
Right.
Sounds great. Awesome.
Okay,
Let's all welcome Ricardo.
thank you.
Maybe this will also be featured tonight.
Yes. Yes, I will feature tonight also,
You're right first.
but yeah, it's a little bit complex. I will read my notes if you dare, so because my English maybe is not so good, so Sonic Earth is a framework, basically. They've been developing to explore how planets' environmental data, like temperature, humidity, air quality, can directly influence musical structure in real time. That's what's. This work is inspired by idea of acoustic ecology as the main cap. Works that has been done from like Schiffer or Barry Trox in the 70s especially. But it extends them to an algorithm and a performative space where data streams become part of composition itself, guiding both the electronic sound and the human performer, made together these two things. So let's see how the system overview it works. The system processes environmental data through a 4-stage pipeline that turns real-time inputs into dynamic soundscapes. The first step is data acquisition and parsing. Environmental parameters are retrieved through live APIs from satellites and these things, like Open Weather, Open Meteo, and more other, because there are a bunch of them. Then I parse them in MaxMSP, then we'll see why, and using custom dictionaries to parse all this data. And all these values like temperature, humidity, CO2, particulate matter, UV index, there are like 30 data of that, are then processed in SuperCollider. Then we see why. So we are using basically two programming platforms for achieving this purpose. The idea is to generate different sound identities. Maybe someone of you is familiar with Sound Objects, is from Pierre Schiffer, Acousmatic Music. The sound object is not has no context, it's just itself. So here we need a context. So we are working with sound, but sound identities. These sounds act as real sound identities. Then we see it. And then, so we have atmospheric layers, gravitational tones, molecular textures like water, things like that, and health-related noise structures, planet health. Each object is modified by perceptual parameters. For example, altitude, its brightness, also the day-night cycles, it's more dark or lose some energy. And finally, we have a cultural layer also, because it's very important how we human interact with the environment. So we have an environmental with sound identities and a cultural layer that interacts with this environment, that that these are the things that interest me. I'm a sound artist and not a scientist, so this is mainly a sound art work framework. Also, if it uses a lot of technology, of course. Let's see now going in deeper and see how these identities are structured. We start with fundamental frequency mapping. You know, in music, we can have a tonal, a tonic, or we may not have. I decided to work with a tonic, like also Schaeffer idea of tonic of the word, but not using a sound, but using energy, the energy of the Earth. And so the rotational speed of the Earth mapped to the latitude will be our tonic frequency note. And above that, we can build all our mental and compositional structure. So we have something to work on. Musically, in translating lower frequency in the polar region, because the tangential velocity is lower, and we have higher frequency to the equator, because the energy is higher. This is a linear map between E1 and E3. So since this work is for performative also, so it can interact with real performers, we see later on, this is cool for double bass, lower notes, or bass, lower notes. So we have a linear mapping range in these things. So the gravitational frequency act both as a music and energy anchor. We have these two. And here it reflects the Earth rotational energy while keeping the system harmonically guided. That's the idea. Now let's see what are above the gravitational, the sound identities are built on. Then we'll hear all of these, and the concert, this will be performed, of course. Once the fundamental frequency has been defined through the Earth rotation, it becomes the foundation for a family of algorithmic sound objects. It's each representing a specific environmental condition. It is my English fine enough, reading like this, okay? Because the atmospheric object translates wind and pressure in broad filter texture, the kind of sound you might associate with motion of the air, for example. Air is one sound identity. The gravitational field object uses a FM synthesis, where temperature defines fundamental tone, creating the slow harmonic pulsation and give a peace sense of weight. The H2O object, water, representing water, the life. All these identities come from my mind, of course. So for someone else could represent something different. So what I'm explaining here is a workflow, a method, not a composition itself, which is a personal interpretation. The water use additive synthesis to represent humidity. Slightly detuned oscillators create gentle breathing pattern like molecular agitation. Rain and snow also are represented. They appear only if it is raining or it is snowing, of course. These are particular. Expressed through granular and formant synthesis, forming particles sound-like. Finally, the environmental health object reflects the overall ecological balance, increasing in dissonance and pollution. That's, we'll see it later. Together, all these objects form the algorithmic ecosystem of sonic Earth, a set of interdependent sonic identities that evolve continuously with real-time environmental data. That's the thing. So now we go through the interaction. then we become all clear when we hear the composition going. The object translates environmental degradation into sound. This is not the standard EQE air quality value. It's a research I did by my own, getting a lot of atmospheric parameters like particulate, ozone, nitrogen, sulfur dioxide, carbon monoxide, aerosol. I normalized against WHO and US and NASA data. And then I check it up. I normalize, did, and check against the real systems. And it works. It gives us a value that represents a kind of health of the planet in that point. All this data is not, it's still a work in progress. So I'm not a biologist, so this is for musical reason, but it represents pretty well the health status. Conceptually, is the sound itself breathes harder under stress, and the EQE reflect environmental condition and influence all the identity. Then we have a cultural layer. So up to now, all the sound identities represent planets, but we add a cultural layer because we as humans live in this planet, and we interact with this planet, and we interpret the planet musically. We live here, and so the cultural layer is very important for the performance and for creating a sound composition that is not an installation or a system. In this phrase, we have a kind that combines cultural and musical heritage to generate geographically defined sound object. The Earth, at the moment, I divided in 8 macro areas. Then it will be more, but for the moment, it's 8 macro plus the oceanic region, which is the macro area apart. If we are not in North America, South America, Oceania, we are in the sea. This represents its own macro area. The goal is not to imitate traditional music, but let local materials like scale and environmental condition influence the way the system works. So basically we have a tonic frequency, a layer of sound identities against the frequency, air, molecular, water, etc. A cultural layer, so which frequency will perform these identities depends on the cultural layer. We have harmonic scales different from every macro region, because it's our interpretation that we live here and we develop Western scales, pentatonics, African, etc. So it's called a kind of spectrocultural identity. The regional scale mapping is what the sound identities introduce as a perceptual human dimension. It connects, So we have regional tradition from different areas of the world, Pacific, Polynesian, and we have also a timbrical synthesis. This is a layer more. I can perform all this layer, of course, during the performance. The timbrical synthesis is like a timbre stamp and comes from Barry Trauck's ideas and also Schaeffer, like tuning of the earth, representing kind of timbrical cultural layer. For example, the bells in the Western part, like church bell, different from the bells from the Eastern. This, I did an FFT of of this kind of sound, and I can perform this during the performance. So regional scales, pentatonics creates the things, timbre stamps, which I can create, cultural layer against all the other things. The EQE, the environment degradation, degrade, how to say, it creates inharmonics on all the system. So if we go in a place where quality, the health is bad, the systems tends to be detuned. The grades of the scale tends not to solve. The tuning of sense of different oscillators tends to not to stay in tune, and so on. So all the system is affected also by the environment, either the cultural and the other. And then we have another layer that is the acousmatic layer, which is very, very interesting. I don't know if you know that platform is Apori. Apori is a sound platform where everybody can go on vacation, can record sounds and put on that platform. It's geolocalized. It's very nice. When I go on vacation, I always record sound instead of doing photograph, and that's why I don't have a wife anymore. And and that's rare, I know. And I put on the Apori also this sound. On the Apori, I integrated the platform in the system so that I can in real time also grab some of these sounds and perform with live electronics. I did a bunch of electronics with Max. And so I can perform also these things together. So I have a lot of instruments. And at the end, we have also the human being, the performative layer. Up to now, all the systems is performed by me, layering the things that we see. But also we have a live performer, which is very, very important for me because this is a work in progress. This is just a zero stage. I have a bunch of implementation which I'm working on. But very important is the performer because we are human, and the human being we use to perform with the ecosystem. At the moment, there is a graphic real-time interface which I created for performers, and at the moment I can use a vocal like a soprano, mezzo-soprano would be fine, and like a breathing instrument like a flute or a saxophone. The vocal performer reads the upper line. On the bottom line, we have like a harmonic layer for both performers. We can see the rotational hair, the fundamental frequency, how the system, the health, this will be more blur. And on the upper, we have for the vocal. I made a research on ancient poems on each of the macro region, like ancient Indian poems or Latin poems, transliterated. And these words come recall when we go in a certain area. It's part of a cultural layer. And also I fragment all the words, and there will be more vocals or more consonants depending if the area is dry in that moment or whatever. So the singer, the vocalist can read this or sing this word. There will be more consonant because maybe we are in the desert and the air is very dry. Sorry. And she knows, or if she must go on extended technique, more unpitched or vocal. That depends where we are. For the flautist, we have a constellation. She can see more or less the notes that the identity number one is doing, but
she don't necessarily have to follow it. It's just an indication. And like for the singer, she knows in a technical, but it's more easy than to hear than to speak. And at the end, we have the conductor layer. This is my work. I create my interface, what I need, with OSC Touch or whatever, and then I can perform and create all my performance, adding layers, mixing layers, and also giving the performer things. So this is the workflow, the general workflow. As I said, this is the overall architecture of Sonic Earth. The workflow is divided in two complementary layers. Problem-solving layer. This is very, very important because I'm not an engineer programming. I'm an artist, composer. And so functional programming is what I need to have an idea that is musical, that is artistic. So the biggest thing, the main thing is to divide problem solving from composition. That's why I use two different systems. Max MSP, don't know if you're familiar with that, which I handle all the main problem I have. That's graphic interface, navigation, API data, parsing, formatting, dictionaries, everything I need. I transform everything in OSC data, messages, and then in Super Collider, which is my compositional tool, the tool that I use normally, I do all the composition. Also in Super Collider, I divided problem solving, so parsing data, OSC, state in its own classes and routines, so that I can have just very simple real-time live coding routine. So all the system is in live coding. And I just have two hands, so I will more perform with controllers, but I can also move the code if I want in all the system. That's the overall system. As I say, this is not, this is just a way of sonificate the reality. I'm doing now with a planet, can be done with anything else. Biology, microscopic beings, aliens, whatever. And it's just a way to understand, to try to interact with reality. Instead of doing years to a psychologist that cost a lot of money, that's what I do to interact with reality. It's a living composition, and the best thing to do is to show the system, hear the system. Tonight will be performed much more, okay? So now it will be a little bit more explained. So let's go here and let's see the thing. Here is the interface, and I navigate through interface. This is the API of Google Earth. I will basically get coordinates to a system, which is that's. I think the problem is the zoom. Let me, because
Okay. Okay. Just a mouse problem. Okay, so this is the interface and this is the composition. Okay, this is all super collider divided from the thing. So let's see how it works. Let's start from here. We get coordinates at the campus, and it is raining at the moment. We can see, we can hear it's raining and also see this little tick tick we are hearing. So I just show you the identity and then we make a tour and I don't talk anymore. Let's see. This is the fundamental frequency. At the moment, it's pretty high. It's 82 Hertz. It's fast because here we are close to the equator. So we have energy. I show you also the score so that we can have a lecture on that. This is the interactive score. We have here speed. Here we have tonal note on the frequency so that the performer knows more or less where it is. And I can give the vocal when I want. This is an ancient poem from Asian. And here I can give the constellation for the flautist or whatever. That's in the case we have a performer, unless here someone is a singer and wants to, no. Okay, so this is H2O, it represent the water, okay? As you see, it's a little bit out of tune and not to solve to its tonic. That's because the quality we have here at the moment is so low. It's a little bit red. This is the health parameters, okay? We are getting CO2, many parameters here in this moment. Here we have a second identity, which is even more untuned. And this identity is directly connected to the quality. So it represents really how a game goes. This for me, it's all performative. I can perform all these things. Here we have precipitation, which appears only if there are precipitation. Rain, it's like this because it is raining. I have snow, but it's not snowing, so it's not the end. Here's the cultural layer, the one that is the timber stamp. We have also the air, but it's not windy, so we are not hearing almost anything. And then I have added, it's not in the paper because every day I add something new. We have also a pulse, say a pulse identity. And it's directly connected to the gravity. Pardon? This is the fundamental, the basic layer of the gravitational hair. The pulse also is directly connected to that, to this.
It sounds the most like some beat or salad.
Nice, yes, the melody are the other layers. H2O, this is the water. These represent the water. It's sine waves that are on beats. It depends how the quality is, the air. Now you hear that are not perfectly on tuned. That's because the air quality is not very good. If we go somewhere in another place in the planet where the air is good, this will be more tonal. Okay, it's also how it goes against the fundamental. It's not only the tuned, but it depends also how it is on the fundamental. It uses a regional scale from Asia, so it's a pentatonic.
Oh,
okay. A scale is a pentatonic. It's different. If you go in Europe, it will be a little bit different. Maybe if it go to a fifth grade, it doesn't tend to resolve to the tonic because the quality is so. If the quality is better, then maybe the cadence will be more. Everything is connected to be more or less tonal. This is the direct quality identity. This one is against this one, or depends on the health and on the quality. This is the rain. This is the cultural layer, FFT in harmonic from here. Air, we are not here, and pulsation. So let's do a little tour and let's see. And let's see. Yeah, we are at maximum volume. Okay. Of course, absolutely. The capital of? Yes, absolutely. Okay. More or less here.
I used to live here. Yeah, so in Ulaanbaatar, it's the coolest and most polluted capital.
Okay. We can also go direct if you give me the name.
So you can.
Or.
Yeah, it's ULAAN. If you look right there. Yes, it's the only city in Mongolia.
Yeah.
I'll talk about that. Down right.
Yeah.
A little to the right. Directly right.
It's that.
Okay, thank you, Maya. Okay, so we go here. It's cold.
Is it snowing? It's very cold.
It's cold.
Yeah.
That's why everything is low, you see.
Yeah.
But from what I can hear, the quality is really good.
The quality right now is.
It's really good because everything is tonic. It's nice.
Yeah, that's true. You're currently not in the city.
Oh, okay.
So once you get to the city, it's in a valley, and there's all this coal that people burn that stays in the air. So the ppm2 levels are like at the peak of the California wildfires.
Oh, I see.
California wildfire air quality.
This is the city?
Yeah, it's something like it's even more. Yeah. Yeah.
This. Oh, we can just write it down. What's
yes, ULAAN.
UL?
There, it's the first.
Okay.
Yeah.
Let's see. Oh, okay. Let's see. It's not bad. It's not bad. Sometimes I check these things when we hear. So, for example, I can call directly here, and so that I can check. Oh, there you see, it's not bad.
Yeah.
But if we go maybe here,
yes.
maybe here looks like this is Norma app.
Curious why the setup here probably a settlement.
Probably here it's worse. Let's see. No, it's not so bad.
Yeah,
You see, everything is changing because there are the things. Okay, let's go, I don't know, to Africa to see something completely different. Yeah, like here. And that's quality is always bad in Africa. I don't know why. Probably it's very dry. Can you see? The water is fast because temperature is high. Its decay is very small because humidity is very low. When humidity, we have long, when it's small, we have this kind of sensation. And we have our cultural layer that is much more, unfortunately here the volume is low, but tonight I will. Okay, and if we, for example, go to Apori now, let's go to Apori and see if someone records some sound here and integrate it in the composition. Code. Let's put coordinates here. Then again, for the live performance, I have mouse and controllers and everything because otherwise it's. Okay. So here in the desert, not very much people record things, but okay, we have we have something here or here. I don't know which is the closest point. Okay, Luxor, whatever. Okay, so we have a little controller here also. Better because with all these zoom and all things, output device, loop back farm. Okay, sorry. Let's see now. And I can perform with this thing. Of course, during the performance, maybe I go down with the other identities. The singer or the flautist may interact with this, for example. Maybe I turn on the flautist, she has her constellation, like that, and so on. So we done, I think time is on, and so we can simply end up to the North Pole, for example, just to end up here. Wind. Low. Thank you. So. Yeah, the performer will be much more
So we have approximately 1.5 hours for lunch. When we get back from lunch, we are making a slight change to the afternoon program. The talk that we could not do this morning from Dylan will start us off at 2. The originally scheduled talk from 2 p.m. will now occur at around 3 p.m. So our afternoon session will last the entire afternoon session length. It is a little longer than in the schedule. If you are a performer tonight and your name is not Roger and your name is not Claire, this is your notice to get lunch and head on over to Soundtrack as soon as you can. Even if your soundtrack is not due for a while, you should endeavor to be there hours early because things we're seeing today always come up. Feel free to check in and then come back. It's just a walk across campus. Ignore Google Maps and go across campus. You'll still run. Lunch should be out in the main area. Thank you all for a wonderful forum session. And let's thank everyone again. I'm going to you on so.
I am your co-pilot, Dr. Dylan Davis, Swinburne University of Technology, Melbourne, Australia. Introduction. This presentation begins with a reflective auditory environment that invites contemplation about the evolving relationship between technology and music. Through an immersive audio-visual experience, the work encourages viewers to consider how digital systems increasingly guide, assist, and shape our creative processes. The title, I Am Your Co-Pilot, underscores the symbiotic nature of this relationship, suggesting technology is no longer a passive tool but an active participant in the creative journey. The foundational concept sets the stage for a deeper exploration of how sound and visuals can be used to represent and interrogate technological progress. Conceptual foundations. The use of multiple drone layers in this soundscape serves as a powerful metaphor of technology's relentless and omnipresent march forward. These consistent and unwavering tones echo the steady, often imperceptible advancement of digital systems that increasingly permeate human experience. By establishing a temporal continuity, the drones reflect how technology integrates persistently into daily life, becoming a background presence that shapes our interactions and perceptions. This sonic metaphor provides a conceptual anchor for the work, emphasizing the subtle yet profound influence of technological systems on our environment and consciousness. Ambient layers in this composition illustrate the evolving nature of music in response to technological advancements. As technology progresses, it expands our capacity for sonic exploration and musical expression. The programmatically mixed audio streams create a seamless, continuous experience that mirrors this ongoing evolution. These ambient elements not only enhance the immersive quality of the work, but also symbolize a dynamic interplay between human creativity and digital innovation. Through this lens, music becomes a living entity, constantly reshaped by the tools and the system we develop. William Gibson's cyberspace. William Gibson's concept of cyberspace as a consensual hallucination provides a philosophical and historical framework for our understanding of our current technological reality. His visionary language bridges the speculative fiction of the 1980s with today's immersive digital environments. In this work, spoken word elements referencing Gibson's ideas offer both historical grounding and contemporary relevance. This serves as a narrative thread that connects past imagings of digital space with present-day experiences, highlighting the enduring impact of Gibson's thought on how we conceptualize and engage with technology. Visual concept, formless and organic. The visual components of this work feature formless and organic shapes that align and react with tonal qualities of the drone. These abstract visuals enhance the immersive experience by appealing to both auditory and visual senses. The shapes represent the intangible nature of cyberspace remaining responsive and present within the digital landscape. This design choice underscores the fluid and elusive characteristics of digital environments, creating a visual metaphor that complements the sonic elements and deepens the viewer's engagement with the themes of technological immersion. Fractal-based visuals in the presentation symbolize a dynamic and unpredictable nature of technology. These fluid, shape-shifting forms embody the recursive and layered architecture of digital systems. Fractal geometry serves as a visual metaphor for technological development, illustrating how complexity arises from simple, repeated patterns. The ever-changing textures reflect the constant state of flux inherent in technological environments, reinforcing the theme of continuous evolution. This visual strategy not only enhances aesthetic appeal, but also provides a conceptual representation of the intricacies of digital progress. The work creates a synesthetic experience by tightly integrating sound and image. The three-dimensional cubes respond to both the mouse movement and real-time frequency analysis with bass, mid-range, treble bands modulating visual behavior. This dual responsiveness blurs the boundaries between auditory and visual stimuli, making them inseparable. The interaction exemplifies the relationship between human creativity and technological capability, where digital systems not only respond to, but also enhance artistic expression. The approach fosters a deeper sensory engagement and highlights the potential of technology to enrich creative experiences. Technical implementation. Granular synthesis is employed to fragment audio into microscopic grains, which are then reconstructed into continuous textures. This technique mirrors the incremental nature of technological advancement, where discrete moments of digital processing accumulate into complex structures. Each grain represents a small unit of transformation, contributing to a larger temporal and sonic narrative. The method itself becomes a metaphor for how technology builds complexity from simple operations, reinforcing the conceptual message of the work through its technical execution. Frequency modulation, or FM synthesis, is used to generate metallic tones with rich harmonic content. These sounds evoke mechanical and electronic qualities of the digital systems, emphasizing their artificial construction. The synthetic nature of these tones serves as an auditory metaphor for computational processes that underpin technological environments. By incorporating FM synthesis, the work highlights the engineered aspect of digital soundscapes and reinforces the theme of mediated reality through electronic means. The voice recordings of Gibson's cyberspace descriptions are processed through programmable filter banks, resulting in dynamic spectral alterations. This integration transforms the human voice into part of a broader sonic landscape, symbolizing the mediation of communication through technology. The processing techniques reflect how digital systems filter and reshape human expression, aligning with the work's exploration of technological influence. The voice becomes both narrative element and sonic texture, bridging conceptual and technical dimensions. WebGL shaders are utilized to generate real-time fractal noise patterns, creating complex and ever-changing visual textures. The recursive mathematics of fractals mirror the recursive nature of technological developments, emphasizing the layered and iterative processes that define digital systems. Real-time rendering showcases the immediacy and responsiveness of these systems, aligning form and function. This technical implementation not only supports the conceptual message, but also enhances the immersive quality of the visual experience. Experience and access. This work is accessible online at thisisnotlondon.com/audio/farm'2025, offering an interactive experience that engages users directly. Controls include a spacebar to start and stop audio streams, mouse navigation to explore the 3D space. Technical constraints such as cause restrictions transform the viewing experience into a form of network participation, requiring users to interact with the same technological systems that the work examines. This participatory element reinforces the theme of technological immersion and invites users to become an active participants in the digital narrative. Conclusion and inquiry. The project concludes with a reflection on the interaction between human creativity and technological advancement. By converging sound synthesis, visual generation, and interactive media, the work blurs disciplinary boundaries and invites contemplation of our digital immersion. The combined audio and visual elements prompt viewers to consider the implications of technology on artistic expression and personal agency. The central question posed, are we the pilots or are we being piloted, encapsulates the inquiry into our evolving relationship with digital systems and challenges us to reflect on our role within this dynamic landscape.
Dylan should be online to be able to answer them. So let me confirm that Dylan can hear us.
Yep, I can hear you.
Excellent. I always love the voice of God effect. I'm going to stop screen sharing so that if Dylan wants to take over the screen, that can be done.
I don't have anything to show, so
You might get questions that cause you to want to show
yeah.
something.
If anyone's got any questions, that would be.
We've got some questions in the audience. I'm bringing microphones around so you can still hear.
Let me just.
Yes, thank you. Can you hear me?
Yeah, I can hear you.
Perfect, thank you. So, like the video we just watched, it's like the subject of the work seems to be really interesting, but I maybe didn't really, get everything like well. So maybe could you state the key ideas of your work once more, maybe in simple words, and also maybe give some comments on the demo we just showed with like the music with these things, so we can better understand the project. Thank you.
Okay. Well, the work's a kind of an ongoing thing, looking at the basically audio reactivity. So it started out as and how that relationship between audio and visuals then represents kind of the relationship between humans and technology. So the idea of the fractal noise background reacting to audio initially started out as a video work, then looking at WebGL to develop that further, and then starting out. So I think that initially started out using just like MP3s made in Ableton. So using some of the techniques I talked about, so granular synthesis, FM synthesis, and the vocal stuff. But then trying to do more and more within the browser itself, and taking it all online, and kind of just getting this relationship, looking at the relationship between humans and technology, and then kind of looking at how different aspects of the visuals and the interactivity can react to the audio as a kind of that as a relationship. So the browser can do a lot more powerful things than video can do, because the browser in there can, well, like using After Effects to generate video, you're limited. But it's within the using Three.js and the Audio.js libraries, you can use FFT analysis to whatever you generate, and then split those frequencies as many bands as you like. So this is split up into, I think, 3 bands. So as you'll notice, as there's more high frequency information, the background fractal changes in response to that. So makeup becomes lighter, or if there's more bass stuff, the background becomes then darker, and it moves a little bit in time with the audio. The audio is generated on a series of timers using the audio JavaScript library. In there's a couple of different synthesizers used, and it also is using a timer to play the MP3 samples. And then the grid sequence of the cubes, that's pretty much taken directly from the William Gibson's lines of light ranged across the non-space of the mind. And when the kind of goes further into how he talks about the data blocks and how it's zoomed up. So that's related to, so that you'll notice that some of the grids are different, the cubes are different shapes and different colors, so as in, or tones more so. So that then relates, the FFT there is also working the same way. So there are base cubes, mid cubes, and high frequency cubes, and they all relate or all react differently to the audio. And there's no actual control. The audio is kind of random. There's no necessary pattern to that, because each timer is slightly different. So it's kind of polyrhythmic in a sense that there's a random note that will play on the FM synthesis. There's the random drones that play for certain times, and there's random granular stuff. And then the random timers for what audio file will play from memory. While it plays, it's never really the same? So it's, I guess each time you press the space bar, you get a unique performance, is one way of looking at it. Does that make it any clearer?
You're getting a lot of thumbs up from the audience, so I think it does.
Okay, good.
Great. Thank you so much for being online, Dylan. I'm very sorry to you and to everyone who for the technical difficulties this morning, but I'm glad we were successful. I'll turn the microphone up and hold it up, and let's give Dylan the round of applause that I hope he can hear.
Thank you.
Excellent. We're now ready to move on to the next talk, which will be about generalizing turtle geometry. So I will just quickly pull it up here and screen share, and then we'll be all set. There are so many cool things running in this browser. Why is that how that works? Give me a second. I just need to collect your actual slides. I need to remember your filing to do that. 125, 5, 12, 10. And are you good presenting like this? Is this good?
That's perfect.
Great. Let me reshoot it then. Option. You can hit on.
Yeah.
Thank you so much. Okay. The conservatory? It's very Googleable. It's the main concert hall of the conservatory. And if you go to the farm website and you go under attending, that's one of the 3 venues. So you can click on that. Alice or Alice? So is it Alice or Alice?
Alice.
Alice. Very great. I'm going to try to hide the meeting controls. How do I hide the meeting controls? Like that. Okay, I think we are probably all good.
Can you hear me correctly?
Oh, well, no, you'll need a microphone. Where did it go?
It's just here.
Well, you'll need to turn the microphone on.
Oh. And now, does it work?
Yes.
Yeah, perfect. So hi everyone. I'm Alice Mixed, and I'm a PhD student at University of Bordeaux under the supervision of David Jana and Martin Laliberté. And today I would like to talk to you about generalizing turtle geometry and to show you a language that is extensible and that allows vector graphics drawing. And it does not work. So first I will try to show you what turtle geometry is, and then I will introduce you the Pandia language, which is a polymorphic language that allows to write multimedia domain-specific languages. Then I will show you the implementation of that language within Haskell. And to finish, I will show you how we can instantiate that language to vector graphics. So first, let me show you what turtle graphics is. So we have a little turtle. It's cute, right? It's heading north, and we can tell it, go forward, little turtle. And it goes forward. It behaves properly. And we can tell it to go left by 160 degrees. Nice. And to continue. And again. And now we're going to name this a squiggle because it is a squiggle. And we can ask it to do the squiggle twice, or 4 times, or 9 times. And after 36 times, the turtle is back to where it was at the beginning. And we have seen all the instructions we wanted to see, which is forward, left, or right, and repeat. Now, there are many extensions to turtle graphics. You can actually do images, but you can also do 3D and music. And in all these extensions, there are some common patterns. And those common patterns are the following. They all use some kind of primitive, like line segments for turtle graphics, or shapes for vector graphics. Those shapes are actually Bezier paths most of the time. Meshes for 3D or musical notes. And these primitives, we can draw them by traveling some kind of state. And this state can be either a space, or it can contain multiple dimensions, including 2D position or 3D position, orientation, rotation, scaling, stroke color, width, stroke width, and for music, it can be pitch, onset, duration, and you name it, any parameter can be in the state. Now, the dream would be, well, what if we can have one language to rule them all, obviously? And this is exactly what I'm trying to do in my PhD thesis. So that language, one language that does that is Pandia. And Pandia has only 4 instructions: the primitive instruction, the state change instruction, the state reset instruction, and the transformation instruction. The primitive instruction allows to render a primitive. So here we just tell the turtle to draw a circle where it is, which is at the origin, and this circle has by default a diameter of 1. The state change instruction tells the turtle to change its state. And here we tell the turtle to move right. So on the image of the left, you see the turtle moving right. And then on the image of the right, we add a second circle where the turtle went. Okay? We can use the repeat instruction from the turtle graphics language to do this 4 times, for instance. You notice that the turtle is 1 to the right to the last circle it drew. Now, the reset instruction allows to forget about any state change that happened within its scope. So here the scope is the whole program actually, and we forget about the turtle moving to the right. So actually forgetting that means we are back to the origin. Now, if we add, after the reset, we tell the turtle to go up and then to draw a new circle. And now we have the following. Great, so can we do more? Yes, of course. We can repeat this 8 times and we get this square of circles. And this is possible thanks to the reset instruction. It has many more applications. For instance, here, I say the turtle to fill the shapes in gray, and I draw lines of circle, and I forget it with the reset instruction. And as you can see, I use the left, which is the rotation instruction, to outside of the reset part. And since it is outside of the reset part, it is not resetted, and we get this kind of wheel. And now for the last and 4th instruction, which is the transformation, what happens is that we can apply a transformation to each individual primitive that is within its scope. So for instance, here, the scope of the transformation is given by indentation, and we draw a line of circles that are all aligned. So we have 30 circles that are all aligned. And we apply a sinus function vertically to the position of each of the circles. Notice this is still Haskell. I'm using the overloaded dot extension. This is a field polymorphism. So you've seen all what Pandia can do, but we've seen like this very specific example. And now I would like to show you the polymorphic implementation, which can be specialized to any kind of media. So this is the monad that represents any media in the Pandia language. So the idea is that a media is a function that takes a state change, the current state, and returns some return value we do not care about, the rendered media, and the new state after having executed the media program. And we have our 4 instructions: the primitive instruction that takes a polymorphic primitive and returns a media, the change instruction that takes a state change and returns a media, the transformation instruction takes a state change, takes the scope of the transformation, which actually is a media, and returns a media, and the reset instruction takes the scope of the reset instruction, which is also a media, and returns a media. Now, how do we actually modify the state? Well, the obvious choice is to use state functions, which are functions from the state2 itself. But sometimes we only want to authorize a subset of those state changes. For instance, we can only want to have linear transformations. And actually, we can have a more general setting, which is to say that the state changes are a monoid, such that there is a monoid morphism from the monoid of state changes to the monoid of state functions. And this can be stated otherwise by simply saying that the state changes monoid acts on the states. So there are some laws. I'm not going to enter into the details. I hope some of you know a bit of algebra, and if you don't, it's okay. So knowing that the state changes act on the states, we can implement the change instruction by simply saying that we simply take the state change and it acts on the state. And it does not draw anything. This is the MMT here. This means we do not render anything. We are just modifying the state. The reset instruction only consists in executing the media that we received, discarding the new state, and returning the old state, along with the rendered media associated. The transformation instruction is just going to compose the current state change given in argument with the context. And we are going to use that context to implement primitive. But first, for the primitives, we need to know how to render a primitive, which means that we must have a function that takes the current state, takes a primitive, and returns a rendered media. So to implement a primitive, we take some polymorphic primitive. We use the render primitive function on the action of the current context on the current state, and we feed it the current primitive. And as you notice, we do not modify the state. So change modifies the state without modifying the rendered media, whereas prim modifies the rendered media without modifying the state. So we have seen this very general kind of media monad. And now how can we instantiate it into a concrete domain-specific languages? Well, you're in luck, because actually we are going to do 3 of them in a few minutes. Turtle graphics, Bezier paths, and vector graphics. So for turtle graphics, the primitives are line segments. For Bezier paths, there are 2 primitives, anchor points and control points. And for vector graphics, we are going to take any Bezier path, and we can use either an open path or a closed path as a primitive. And here you can see actually 2 primitives, which are both closed paths. So which rendering monoid should we use? Well, for turtle graphics and vector graphics, we use superimposition. And for Bezier paths, we just use path concatenation. Actually, we just use list concatenation. So that's very simple to implement. The superimposition can be simple concatenation of strings because I'm simply rendering to SVG. Now, how about the states? Well, for turtle graphics, we can use affine matrix, which will contain position and orientation of the turtle. We actually get more for free, like scaling, and whether the pen of the turtle is up or down. For Bezier path, we only keep the affine matrix. We do not care about the pen. And for vector graphics, we could actually add anything we want, but here we use fill color, stroke color, and stroke width. So today, for the sake of simplicity, I'm only going to use the state functions for state changes. And here, for instance, the rotation is a state change. We can implement it by simply multiplying a rotation matrix with the current state. But what's interesting here is that I use field polymorphism. And this means that this rotation state change is polymorphic in the state, as long as it has an affine field. And this is interesting because if I want to implement the left and right instruction from the total graphics, well, then actually it remains polymorphic in the state. So we use the change instruction, and we use the state change we just defined, and we get left and right, and it is polymorphic in the state, which means that we can use these instructions with any media that has this affine field. And this means that any of the languages I just defined, which all had this affine field, as you remember here, can use the left and right instructions. So to finish, how do we instantiate correctly the media monad? Well, we feed it the change, an instantiation of the state changes, the states, the primitives. For total graphics, it will be segments and so on, and the rendering monoid. And since the media, the monad I just showed you is actually a writer monad, we can execute it to get the final rendered media. So for instance, we can implement an approximation of a circle by repeating 4 times the drawing of all these control and anchor points. But it gets better because we can use the code I just used before as a primitive to the vector graphics language. And we do that by simply saying, oh, we use that path as a closed Bezier path. And now we can use this circle syntactic sugar as monadic actions, which draw a circle. So here I say to the turtle, okay, now your state is fill red, stroke black, and you draw a circle. And then I say to move down and to fill in blue, and we get a square. And the square is defined the same way the circle is defined. So what to remember of this talk? Well, if you want to define a domain-specific language using this Pandia language with only 4 instructions, what you need is a rendering monoid, a set of states, a set of primitives whom you need to know how to render, and a set of a monoid of state changes that acts on the states. And if you have that, you will be able to define any kind of syntactic sugar to create your own domain-specific language. Now, if you have any suggestions, any ideas, or any questions, I would be happy to answer them. And thank you very much for your attention.
Yes, it was for specific. So I have a question. You showed examples with images. Possibility about And also you should you show that we can use circle in different domains, and how would circle sound or
Yes, so in fact, this is like just the beginning. I'm currently working on a real-time version of this. It's quite advanced, actually. In the case of music, well, basically here we have 3 different languages, and you can imagine that instead of, for instance, if you remember the states here, well, you could also put pitch and onset time and duration. And if you look at this rotation thing, well, you could write something like transpose. And this transpose thing would be, you could write some syntactic sugar with the transposition. So basically the turtle, instead of traveling a 2D space, it would simply travel more D space with pitch, duration, its onset time, and so on. And then if you know a bit of Haskell, well, you know that we have GHCI, and then this media thing can be actually put into the IO monad, and you get a REPL for free where you can play music. So this will be next year.
Just in the interest of time, I think we'll take any question. Well, one last question once Stephen gets up.
Okay, so my question is, so the code that you showed us, that is medium and that you implemented yourself, go ahead with the code. But of course, a lot of these definitions you could get for free by using some library monads. I think if you use region writer state.
Yes. Yes.
So is there any reason that you're making your own from scratch instead of taking a stack of monad transformers?
Yes. Well, for first, stacking monads transformers is inefficient. So that's the main reason. And second, the thing is, sorry. Yes. The thing is, indeed, you can I get my thank you. The thing is, you could actually define this. This is a reader monad. This is a state monad, and this is a writer monad. So you can make a monad stack transformer. But in fact, what I'm not saying is that all this is inside a class and in a MTL style. And it does not really matter since it's inside a class. So it's a good question. But I renamed those so that it also makes sense for what I want to do. Thank you for your question.
So that's all we have time for on the questions. Thank you so much. I'll need to take that one. Here you are.
Thank you.
We will unmute your laptop now.
Shall we put the this on top of the speaker, or should I attach it to my?
I would recommend attaching it to yourself.
Okay.
I do need to mute you because you are currently having two machines. Just mute me.
Good.
Great.
I'm now unmuted. Although I can hear myself.
That's because I'm hearing the laptop.
Oh, okay, that's from the laptop. Very good. Okay. Hey. So for the remainder of this talk, I'm going to just give a live presentation in Jupyter Notebook of setting up some different patches and taking you through the basics of using the combinatorial audio workstation to make some cool sounds. And yeah, so I only found out a couple months ago that it's possible to do Rust in Jupyter Notebook. There's a library called EVXCR that makes it possible, which is pretty cool. It's a Rust REPL. And I was originally, the video that I submitted for this is a live coding session where there's multiple different cells with sound in each of them changing over time. But I think for this talk, we're just going to keep things a bit simple and go through the basics. And by the end, we'll have something that sounds pretty cool. So this is just some boilerplate, which I've already run, that creates the output node and the ship button. Just so that we don't blow up the speakers. We're using my laptop speakers, so it doesn't really matter. And let's start with something simple. So the primitive type that all of the modules in the synthesizer implement is this SIG-P trait. It's just things that can be sampled. Modules are sampled not at the audio sample rate, but once per what I call a frame. You can change the length of a frame. It's usually maybe about 20, 30 times a second. And this sample method populates a buffer of the appropriate size given the frame rate and the sample rate. It's done that way so that we can take advantage of some architectural optimizations. So let's start with a simple hello world. Everyone's first synthesizer patch. We'll just play a sine wave at 200 Hertz. It's already playing, but I've muted it. The 200 Hertz sine wave. Let's turn the volume. It's already up pretty high. Oh, it's okay. Sine waves are high. We can change the waveform by changing this to a different value. It's a little bit cumbersome to change the number, so instead one tends to use a knob. And this is going to pop up a new window. Now, you'll notice that there's a lot of this build after everything. And this is because most of the modules in this library have optional parameters, same defaults that you can specify if necessary. And using a builder pattern in Rust makes it a lot more ergonomic. Only add the methods that only change the properties that you want to change and leave the other ones with their default values. So one example of that is the pulse width of the pulse wave form. So we change our waveform to be a pulse. Now and so a knob is also a system that just always yields the position of the knob. And so this works because we can obviously put a fixed number in one machine. It's not going to be and the reason why we can exchange numbers and ones is of course because almost all of the arguments to parameters modules here's a more complex example. So here what we're doing is there's two oscillators. There's the pulse wave oscillator, the automated oscillator, using the sound. The second oscillator is modulating its pulse. And so this knob is controlled is modulated in my house. Not getting faster. Now, we can do arithmetic on signals. And this will just do the corresponding operation on the pairs of values on either side of the arithmetic operator. And this makes it really easy to do stuff like make a mixer. So here we're just creating two oscillators, a saw wave and a pulse wave. I am using a shorthand here rather than using the oscillator function as a helper that just creates the wave of the given shape. So this is a pair of oscillators added together, roll over this, and then roll over and right, and everything else, but to multiply them together scale, we'd be doing what's called FM. One way can act like area, and the other way to modulate that. I mean, listen really into the sounds as well. Especially when the frequencies are very similar. The one particular beat pattern that's very common in is when you take a pair of saw waves very similar to add them together. Every time I reevaluate a cell, it goes to family of where inference they sounded very different from a single wave on the phone. See how different it is. Let's play this one by kind of going down. It's an entirely new text. It's common that I've got to have a superstar of its which creates a set of signals at a configurable number. And performance reasons that some the see, it gets quieter because the number of stories that move each other destructively reduces the average code. Again, it might have more possibilities. Okay. So the next concept to introduce is filter. We've already seen examples of signals that are modulated by other signals with output modulation changing. And to help make this kind of signal, I don't make it have a signal which is fully in the process, which then produces a new signal by modulating. Core has a method called filter, which you can use to chain together a sequence of transformations on it. Let's look at a simple example of that first. Band pass filter. We're gonna make 100 Hz saw wave, and then pass modulate. Filter has to not as doing a little harmonic from it down by outside of its if you think of the FFT would look like you're kind of standing down with and then moving outside as not all the way down. All you hear are bass harmonics, or the bass frequencies from the waveform. Out of that, higher. Want the filter to be very narrow. It's a shame. Oh, I guess we can turn it on. So when you make it really narrow, you can isolate individual harmonics, and so you can see the different harmonics of the saw wave one at a time, it really helps you understand more about why a saw wave sounds the way it does, and you look at the frequency, you look at the formula for how to draw a saw wave, and you see that it's made up of different integer harmonics. And now you can listen to them one at a time. Let's look at another example. This time we're going to use a low-pass filter. They're very similar to the bandpass, except now it only removes the high frequency. The reason I introduced that pin is because it's a second knob controlling the resonance, which you imagine a filter removing everything above a certain frequency. It can also add a little boost to frequency around that quite common in the pass filters used. I also don't know if this is an implementation artifact or found aesthetic. See more of that in a second. The final one is a little more complex. So we're going to take the previous example with our oscillator going into a low-pass filter, except instead of the saw wave, we're going to use the super saw wave. And then this final filter I'm adding is a compressor. The behavior of a compressor is to clamp all of the to a button press and sends a pulse of a certain shape, as though a knob was being turned by that. So I'll run this example and then explain what's going on. Okay, so this time we have a button. When I press the button, I'll turn the volume up a little bit. So this envelope has two properties called attack and release. The attack controls how long it takes for the signal to ramp up to its maximum value, and the release controls how long it takes for the signal to ramp back down to 0 when the button is released. So if I turn the attack up, and I turn the release down, and then I press this button, and then when I release it, it cuts out immediately. All right, if I was to return the attack down and the release up, we see the opposite. And so you can use these settings and others to change the way that a note comes on or off when a key is pressed on a keyboard or a sequencer chooses the next note. So rather than pressing a button manually, as we just established, we like to automate things. So here we're going to automate button presses with a clock. So 8 times a second, this clock will send a pulse to an envelope, which will modulate a supersaw wave. And we'll get some knobs that we can use to control the properties. But the windows take a little while to start sending signals back to the synthesizer. We'll use this meaning internally, by the way. Every window is a different process. by sending commands immediately. Seemed like the most cross-platform way to do. Happening here is that you'll notice there's no attack anymore, just released, and that's because the button press is being automated with the plot, which is just sending a pulse, which means that the attack would have to be 0 or we wouldn't hear it. We wouldn't be able to round up control the release. Release down the length of the notes. For constant washy sound. All of our sounds from scratch every time. There's a couple of handy built-in patches that to every for things that are a bit more complicated than melodic stuff like we've seen so far. So the drums, rather than using pre-recorded drums as option of synthesizer drums, really just has 3 right now: kick drum, snare drum, and a hi-hat. I'm just looking at those first 2. So is it very quiet? Turn that off. We have snare. They're also quite parameterized. I don't know how. Is Jupyter going to let me autocomplete? Okay, I don't remember the names of the parameters, but there's lots of settings you can change about the way these sound if you want to tune them for a specific application. And of course, we don't like pressing buttons, so it's very easy to automate these. This button is obviously just a signal that produces a Boolean, much like our clock from before, so we can do the same thing as earlier. So now, this is just setting a, so this is using the concept of a clock divider. Is that okay, cool. So skip on to the sequencing. So to play actual songs, could play them manually, but instead like program in a sequence of notes and then send those set those to be the frequencies of the oscillator. So I've pre-programmed a riff that I kind of like. So just using the triangle wave, a simple ADSR. Exciting. It's showing how we notes and then we can turn those notes. And then if you take everything we've seen so far, I think that's all we have time for. So just put there's a bunch. Obviously, we're only scratching the surface. We can do with cool. Yeah. Thanks everyone.
While we wait for our last meeting, so how is that one question? More on the machine.
Yes. Could you briefly compare with Super Collider and tell us maybe, I saw that you were referring to FRP and how FRP differs from the graph version of Super Collider.
I've honestly never used Super Collider, sorry.
Yeah, can you tell us about how FRP can be applied for that?
Sorry. Yeah, totally. What's the
I know what's going on. Wait a moment.
I guess you mentioned the graph in Super Collider, and
It's just a big tree, right?
yeah, well, it's a DAG. You can have sections that rejoin in core. I didn't show any examples of that here, but the one hairy part of that is in Rust with the burrow checker, with like Rust linear types means that you have to use a little bit more syntax in order to do that. You need to say that a node is shared, which allows it to be cloned. And that has to happen explicitly. You can't just implicitly take a node and refer to it in two places because new semantics would not allow that. But Core has an API for boxing signals that makes it possible to do that. You want the microphone?
Yes. But it's your confidence talk, so I'm telling her I get to be concerned. You small one you want.
Yeah. Oh, yes.
Yeah, there you go.
Oh, sure. Yeah. Oh yeah. Tab. Other control tab. Yeah. I'm gonna go ahead and close these tabs if that's okay. Yeah. Yep. And so yep. Cool. Okay. Yes. So my name is Matthew. I'm going to be presenting basically a web-based like interpreted language, very much modeled after Haskell, specifically designed out of my kind of experiences with TidalCycles and my live coding performance practice. There you go. Okay, cool. Yeah, there you go. Yeah, a little bit of background. I come very much from the sort of art and tech side of things. I have a background in visual art, also in music. And I have always worked with various forms of computational art, and most recently in the last 5 years have done a lot of live code performance, which, if you're not familiar, is basically the process of writing code that runs some sort of generative musical or generative visual system. And as you are writing the code, you are updating the system in real time. Like here, you can see both the code over these visuals that I'm generating with the code. And yeah, and so I'd also like to thank my co-author, William Payne. He is a frequent collaborator of mine over the last couple of years. He has a background in sort of music and CS education, particularly accessibility and kind of design for education. And
we've worked a lot with this language TidalCycles and worked with a group of blind and low vision music students in a laptop ensemble using TidalCycles. So what I will be demoing, Weft, is a piece of software that I've developed, although my co-author has greatly shaped my thinking about live code tool design and a lot of how to present this project as well. So TidalCycles, like I mentioned, is a very popular tool for performing live coded music. It is written in Haskell, and as a result has, I think, introduced Haskell to a lot of people who never would have touched it otherwise. You know, it looks similar to this. This is very sort of idiomatic Tidal code. Ultimately, my system sort of re-implements a lot of these sort of syntactic features in a web-based environment. So I will cover more of the details in a bit. I will point out one feature of TidalCycles that you see a lot is this mini notation, which is a way of expressing patterns of like sounds or numbers, that sort of thing, in a small domain-specific language. In the context of Haskell, this isn't actually being represented as a string, or rather interpreted as a string, but using the overloaded strings extension in GHC. This is a proper kind of member of the pattern type, which is a broader type that can be used to represent a pattern of any sort of value that happens during various events over time. So the mini notation is a way of expressing kind of easily parsable pattern values, so patterns of strings, patterns of numbers, that sort of thing. But you can also construct patterns of functions, patterns of patterns, through sort of more normal Haskell methods. So when you run TidalCycles, you are really running a somewhat complicated stack of different tools. So TidalCycles itself is basically GHCI that's being hidden away underneath an editor plugin in a code editor. And so you will see someone performing with something that looks like a code editor. And really what this is just an interface for taking blocks of code and secretly sending it through standard input-output to GHCI, which itself has been running probably some sort of, oftentimes it's called like a boottitle.haskell, sort of just a script to actually start the system, and then it imports this TidalCycles library. And then that itself sort of sequences and generates and manipulates patterns and then sends the output events as kind of OSC, Open Sound Control instructions to Super Collider, which then also has a third-party library that you have to install. Needless to say, this is often pretty intimidating for potential live coders, particularly ones not coming from a tech background. And so, so naturally, it becomes very attractive to, move this online. And there's a sort of obvious question of like, why not build a live coding system that is more easily downloaded and installed and used? Either I mean, there are certain things like Sonic Pi, which is a standalone sort of wrapped application, or or a sort of proper kind of web app. So that has led to the development of Strudel, which is an existing library originally begun by Alex McLean, the creator of TidalCycles, and then a variety of other contributors, particularly Felix Roos and Jade Rose, have made huge contributions to it. And essentially what it does is it implements all of the underlying data structures and algorithms, but purely in JavaScript. And then also it adds this very sort of idiomatic JavaScript kind of DSL that, just because of how the sort of functions work, happens to be about, sort of mirror image TidalCycles for a lot of things. I'll note here a couple of things. First of all, we still have the mini notation, but also we're making heavy use of this method chaining to kind of, sequence functions, although that's mostly a quasi domain specific language. Basically, these are, true to their Haskell roots, these are essentially pure functions, and the chaining is mostly a kind of mechanism where this one object gets passed around mostly for the convenience of, writing code like this. But certainly for me, I was a little sad to see the move away from the typed strictness of Haskell, which offers a lot in the way of reasoning about your program, kind of thinking through pattern manipulations as a set of pure functions. And so what I have been working on is basically building a Haskell-like interpreter so that I can take all of these functions that have been implemented in JavaScript in the Strudel library, but use them in a typed kind of functional style a la Haskell, and then use that as a test bed for developing kind of better editing and performance tools around that. So a quick tour of the state of kind of web-based live coding. Strudel is an example of the predominant strategy, which is basically you have an editor, you can write JavaScript, the tool exposes some specific JavaScript library, and you run it, but under the hood, it's just eval, running eval on the code that you're writing, and it can support arbitrary JavaScript. This is Hydra, a visual tool made by Olivia Jack. This is, like I said, Strudel adds a little bit on top of that. For example, instead of Tidal's functions that allow you to sequence multiple tracks, it uses labels in a kind of tricky way in order to approximate that. It also has this feature where it highlights events in the mini notation so that you can see your pattern as it's playing. And also it has some inline visualizations like this piano roll. And to a large extent, these these kind of draw off of other experiments. Another system, a similar system, is Charlie Roberts' Gibber, which has a whole host of kind of sophisticated visualizations. And I think that these are great as far as live coding is concerned, but still, these both here and in Strudel, they use a JavaScript parser in order to figure out some of what's going on, but there's a limitation to how much you can, augment your code based just on, a parse analysis versus an analysis of a type system or of, the sort of full scope of what things are imported from where, that sort of thing. There are also web-based languages that are, kind of have their own compilers. One of actually the first, sort of attempt to bring Tidal to the web came in the context of Estuary, this project by David Ogborn that is a multi-user live-coded kind of platform. It supports what it calls mini Tidal, which in that case is implemented in Haskell, takes the original Tidal library of functions and moves it to the web, though as a consequence, it relies on a very strict set of functions and this kind of constraint that every single one of these boxes is a single expression to be evaluated. So it is sort of type safe, but just at the syntactic level. And so it isn't extensible in the same way that JavaScript-based systems are. There are various other related languages. I mean, there are other kind of typed languages that compile to JavaScript. I mean, Elm and PureScript, drawing from a pure functional background. TypeScript is using JavaScript plus type annotations. They're generally not designed for running in the browser. TypeScript theoretically could be, I think, though I haven't really seen it used much. I think because it's a pretty complicated piece of software and using it in the live coding context would be tricky. I'll say there's also Hazel is probably the closest thing, which is a live functional language, not from the live coding community, but from the live programming community, which is an entirely distinct research community. And I am really looking forward to the Paint workshop on Tuesday, I believe, which is going to be sort of that community of people. And so what I've built is basically a parsing and type checking library. It implements a small set of Haskell language features that I'll point out. And in my example, it's an editor application. It starts a runtime instance of this library, and you can use that to check and evaluate code. There is a sort of a strong distinction between the library, or the editor allows you to execute expressions as sort of statements, and then if you want to do bindings and actually add things to the environment currently, you do that separately, kind of with the library runtime itself. But it's a pretty simple process to add new bindings to JavaScript files. This is some TypeScript code. It doesn't even need to be that. And it implements, just the straightforward $ function application operator. I'll note that the internal representation of types is ultimately, a more complex structure, but this function has the nicety of parsing type signatures as well. So in its kind of current version, and it is currently live at weftcode.github.io/weft, and it includes pretty much the entire Strudel library, or at least as much as I have bothered to write type annotations for at this point. And although the system itself is very agnostic to that, and absolutely could and I think should be augmented with new functions and new bindings to functions. Okay, so I'll briefly show a few things in terms of the kind of the editor itself. Yeah, so here we have a very simple pattern. Everything sort of in TidalCycles operates on the cycle, and right now this is just one bass drum per cycle. I can edit that, let's say a wood block or something. And the second while it loads, and then, because we have a type checker here, in our editor, we can actually inspect the different types. Like I said, it understands that this is not a string, but actually a sort of overloaded string, and that this is in fact a pattern based on the fact that the S function, which turns a pattern of strings into a pattern of controls, these are like annotated synth controls. It expects a string. There are various polymorphic functions. So the fast function, which speeds things up, is implemented for any pattern ultimately. So in this context, we have it inferred that it's a pattern of controls, but also working, within the context of this pattern here. Here we can see, we've got various type errors. Oh. Yeah, I know that's why, because that needs to go there. And so then in this context, now this is a pattern that operates on patterns of strings. And I'll go ahead and kind of play some more, complex patterns. And so you can see, this is basically in kind of Tidal idiom. You have a set of functions that are modifiers of patterns. Usually they use the forward $sign operator because it's a way to avoid parentheses, which is nice. And then at some point you have a sort of primary structure that's this N pattern, which is a pattern of, in this case, scale indices. And then you can kind of have patterns after it that are sort of joined together. This hash is a pattern combiner. Yeah, and so basically the system, supports function application. It supports lambda expressions and sections, operators, that sort of thing. And yeah, I will very briefly sort of run through. Right now it's mostly a kind of simple system for, running Haskell-like code. Eventually I would like to add new language features, new syntax, potentially expand the type system to use proper overloading via type classes. And, longer term, I see this as a base to explore the question of what does a properly live language, where you can have a deep integration between the language and the environment. What does that look like? Cool. So thank you so much.